Good afternoon, everyone. This is Rich Medairos from TACO. Today's presentation will be a deep dive into HVAC pump fundamentals presented by Brett Zerba. A few housekeeping things before we get started, a little bit about our company. TACO is a family-owned company owned by the White family, and it's been in business just over 100 years. I think actually we're 102 now, aren't we, Brett?
Yeah, imagine that. Well, it was 100 when the 2-week shutdown happened.
Yeah, I know it. Couple of things we want to talk about is that we do have some handouts. If you'll notice on your screen, you can download. There are 4 handouts that you can download. Several of them on IOM manuals. There's a mouthful. I always have trouble with it. IOM manuals. And there's another one on seal face material comparison. So the great support information for today's presentation. If you have questions, I will be monitoring. I'll be the moderator for today's discussion, and I'll be looking for your questions. So if you have a question, just type it in, just to make sure that that part of our system is operating properly. If someone could just type in a question in the question area that they can hear me and see our screen okay. You should be seeing the green leaves with HVAC pump fundamentals. Yep, I got a few okays. Looks good, sounds good. Well, we're in business, Brett. So in a few
Excellent.
seconds, I'm going to turn it over to Brett Zerba. About questions, you can ask questions in real time. I will ask Brett to pause periodically, and we'll ask the questions. We will have some time at the end of the presentation also to ask questions. We like to try to make this as interactive as possible. So please type in your questions in real time. And like I said, I'll ask Brett to pause and we'll try to answer as many questions as possible. If I see multiple questions that are the same, I won't ask, all the variations of the same question. Usually I'll just ask one of those. So I think we're all set. Brett, I'm going to turn it over to you and let's get started.
Thanks, Rich. Appreciate that. Hello, everyone. Hopefully you can see my hello on the screen. I'm practicing making sure I can do some writing here just in case I want to do that during the presentation. As Rich said, my name is Brett Zerba. I'm a application/training engineer / whatever at TACO. I've been with the company over 25 years now. Hard to believe. I blinked and it's been 25 years. Pretty crazy. And the last 2 years have been as nutty as any in my career. I graduated in 1981 from the University of New Hampshire.
New Hampshire. Is that how you say that, Brett?
New Hampshire. Yeah. I grew up in Connecticut, went to school in New Hampshire, live in Massachusetts, work in Rhode Island. So people say, well, you can't really tell where your accent's from because it's all screwed up. Sometimes I park the car in Harvard Yard, and other times I talk like a New Yorker or Connecticut person. Anyways, I digress. So today's presentation is on HVAC pump fundamentals, and it's going to be pretty basic, but we'll cover some in-depth stuff. And we'll talk about other presentations that I want to make sure everyone's aware of. So, and when we say HVAC pumps, the pumps that we manufacture, right? And we actually manufacture them and assemble them right in Cranston, Rhode Island, for the most part, which is a U.S.-based company, manufacturing firm. But anyways, these pumps move water, hot, cold, and condenser, for the most part, right? And maybe there'll be some glycol in it at times. I see my friend Tay from up in Alaska. I'm sure he gets involved with glycol systems on a regular basis. But for the most part, these move water. They're not industrial design pumps, although we do have an industrial division that I'm going to talk about a little very shortly. So that's one of the biggest fundamentals to make sure everyone understands. Our equipment heats and cools buildings for the most part. For the most part. So let me try to erase this. Let's see if I can figure this out. Erase all drawings, and let's get going. So what is the function of a centrifugal pump, right? And that's what we call these pumps here. So internally, there's not a lot of moving parts. My good friend Rich likes to point this out when we have folks in front of us, which we're going to start doing in April or May or again this year at our factory. Can't wait.
Yeah, we're going to have real live people with. We're actually, it's like having a farm. We don't have virtual cows. We have real cows and real sheep and stuff like that. So
we did a practice run with about 25 people in October because we were really getting geared up and we were going to do some more. And then what variant was it? Omicron? I don't even know.
Was it Omicron? I don't know what variant we're up to these days. Did
shut
they
us
give
down
names,
again, so
do they have names for the latest variant, or are they numbers?
Don't get me going on that. Don't get me going on that. But anyways, internally, as it rotates the components, it's an impeller, right, and a shaft. Those are really the only moving parts, and they create a differential pressure or a delta P, right? This is some terminology that you have to get used to. And then internally, the water flows from higher pressure to lower pressure, right? Nothing earth-shattering there. It's all pretty basic stuff. If some of you have taken some fluid dynamics courses, some of this may make sense. And then that delta P induces flow against system resistance. So us engineers, Rich and I get involved with this quite a bit. You have to do system resistance calcs to help size the pump, right? The head loss, the differential, all of that, the terminology you have to get involved with. So that's very, very important. Now, most of the systems that our equipment goes into and you folks work on are what we call closed systems. That means they're not open to the atmosphere. So think about a 4-story building, right? In the boiler room or the heating generation of components are down in a room downstairs or in the basement or whatever, and they push water around the room, around the floors, 2, 3, 4 floors up and back down, but it's not open to the atmosphere. It's a closed loop system, okay? But some of our equipment are installed on open systems. Okay, that's like probably the most common one is a condenser water / cooling tower type system. So in that type of system, that you also have to worry about lift. Okay, and I'll talk about that a little more when I get into another screen. So not necessarily in a closed loop system, you don't have to worry about it, only for the pressures, but not for your system resistance. And then as an engineer, you need to calculate the flow and head required to properly select the pump. Now, we're not going to get into the calculations of that and how to do those calculations. We have other presentations on that. Our head the process Rich goes through for the head loss calculation is very, very basic, point to point. But that's not today's presentation. But you do need to calculate that information. And then eventually you need to create a pump schedule. And look at this one that's on here. It has TACO pumps listed. Well, that's nothing wrong with that.
That's convenient, huh?
What's that?
That's convenient that they're TACO pumps.
Yeah, since TACO's sponsoring this webinar, they should be. You could take this and have it as your basis of design right here. What do you think of that, Rich? I brought in the basis of design. We won't even get into that whole discussion.
Isn't that what Henry Ford said? You can have any color car you want as long as it's black. So we could have the same thing. You can put any pump you want in the schedule sheet as long as it's TACO.
There you go. There you go. So anyways, just some basic information that you got to talk about. So I want to cover closed systems, okay? Chilled water type systems, cooling buildings through fan coils. The new craze is maybe some chilled beams or whatever, even through some air handlers. These are closed loop systems. They're not open to the atmosphere. That delta P, right, induces flow against system resistance, but no lift. There is no lift. So the height of the building comes into play for pressures and length of pipe and volumes and all of that. But the height doesn't necessarily, there's not a calculation added to the system resistance for that. Sometimes people, ask that question how does that come into play? So you got to calculate all of the twists and turns and the elbows and all of that, but no lift per se in a closed loop system. And again, that's most of the systems that these HVAC pumps are installed in for the most part. Open systems, what we call open to the atmosphere. Something is open to the atmosphere. And again, I mentioned this a little earlier, probably the most common type is a cooling tower, right? An open cell cooling tower, which might be providing some water to help cool the chiller, a water-cooled chiller type of system. So that's open to the atmosphere. So you have your system calcs for the delta P, you have your piping and fittings and valves and all of that, but then you also have some head or elevation change for that from the bottom to the top of the tower. So some stuff to consider in that regard. And again, we're not going to cover NPSH in that much detail in this presentation. Rich has an incredible presentation on net positive suction head that really gets into the Goldilocks planet, right, Rich? Don't we talk about the Goldilocks? Goldilocks.
Yeah, we did a presentation of, I think it was like 3 or 4 years ago, and I said, does anybody know the story about Goldilocks? And someone in the class said, well, isn't that the girl that has the hood and she runs into the wolf? And I said, no, that's Little Red Riding Hood.
That's
so
true.
Goldilocks mixed up with Little Red Riding Hood.
So anyways, you know, Rich and I, as we work for pump manufacturers, we've had different careers in the past. So we tend to recommend you do the NPSH calculations for closed, open, or any type of system, because we don't want to have any issues with that once these pumps are sent out there. But nonetheless, please make sure someone on your team, design team, and Taco's more than willing to help. Our reps are offer help as well. Do the calculations in an open HVAC system. So if you have a cooling tower, if it opens to the atmosphere, do the NPSH calculations. Save yourself, at least take it into account. What do you think about that, Rich? Isn't that some good advice?
It is, yeah, I would.
Anyways, let's keep going. So here's a cutaway of you know, and some principles of operation of a base-mounted pump, right? And some of the terminology, some of the fundamental terminology inside of there. So you could see let me get my little bouncy ball here, little spotlight, the suction, right? That's right here, and that's actually the eye of the impeller. That's where the water goes in. The volute. In our industry, most of them are cast iron. You might see some stainless steel ones on some of the smaller ones, but for the most part, it's a ASTM 838 or some cast iron type of product that makes up the casing. Some people just call it the casing. Some people call it the volute. So there's different names, and that's one of the things. You know, when you get involved with this industry, you might get in phone conversations, and people may just say volute or volute casing or whatever. Wet end. They may even say wet end. So just learn all the terminologies there. And there's the impeller. And you see the vanes. These are the vanes right here. You can see they have a nice little curve to them. I think there's 8 in this one here, and that's very, very important internal design component of the impeller. And our R&D engineers work very hard when they design new pumps on the curvature and how many vanes there are and whatnot to make sure that you're going to get the highest efficiencies that you can out of this pump product. And by the way, we're very proud of our base mounted and our vertical inline pumps, and I'm going to talk about the inline verticals shortly. We have leapfrogged the competitors for our efficiencies. Our basis of design, our efficiencies have leapfrogged them, so we're very, very happy with that. And nonetheless, diffuser or throat, that's where the water comes out. Discharge, most of them are flanged. I think probably 90+%, 95% of them have flange discharges. And for the most part, the flanges are rated at 125 PSI, 125, but you can get 250s if you require on a high rise or something like that. So that's something that you have to make sure you take into account. And then there's the cutwater. That's where the water kind of gets separated from the impeller and finds its way through the diffuser and out. I got another picture that'll show you it a little better. So that's the Cutwater there. And impellers now, most of them are bronze. You have some options for stainless steel. For the most part, they're bronze, and they have a what we call a maximum trim and a minimum trim, and trim anywhere in between. So what that means, we call it trim, cutting it, whatever. That means you actually grind off part of the impeller to get a certain diameter, right? You have different diameters for the impeller. The maximum trim impeller will give you the best efficiency point, because your clearances, your highest efficiency is when the impeller, this clearance right here, is as small as can be. Otherwise, as you make this clearance a little bigger, right? Think about it, it gets bigger, you get a little more recirculation in there, and that causes some losses internally that will affect your efficiency. So stuff to consider. These impellers, and most of the stuff I'm talking about is common for all pump manufacturers. These impellers are trimmed at our factory, or they can be trimmed at our reps based on diameters, and they're balanced. So they are properly balanced to a Hydraulic Institute standard. And they actually, if you're familiar with how people balance tires, companies or whatever balance tires, they may put little lead on them, pieces. We actually take metal off of, we'll grind a little bit of it. So some of you have been to our factory, our impeller trim machines on one side and the balancers on the other side. It's sitting right there. But nonetheless, there's some basic information about the impellers and whatnot. And then,
So Brett, we do have a quick question.
Oh, great.
Yeah. So the question is there ever a reason to trim an impeller if you have a variable frequency drive?
That goes right to the heart of
yeah, I thought that would be a good question to ask at this point, but that's a great
question. There's different philosophies on that, and you could have 6 people in the room, and 3 could say one way and 3 could say another. My answer is yes, but not always. What I mean by that is it really depends on the design point and how much you have to trim it or would be trimmed. If you start thinking about it, I'm going to make up some numbers here. This impeller that's shown on here could be maybe 11 inches in diameter, and the minimum size could be 8 inches. Well, if you pick a design point that's closer down to 9 inches or whatnot, and you leave it full trim, you're not going to get the proper when you start slowing the speed down, you just aren't going to get the savings that you expect. Can you expound on that a little bit, Rich?
Yeah. Why don't you repeat what you just said, Brett, to make sure I'm commenting on the same thing?
Well, what I was saying is when you have a maximum trim impeller, right? Someone asked, the question was, do you need to trim an impeller if you have a VFD on it? And the answer is yes and no. Not all the time, but if the design point that you pick a pump for, and the design point gives you an impeller that's probably close to the minimum diameter or whatnot, you may want to trim it in addition to having the VFD, just to get the savings that you want. But most of the time your design point's probably going to give you on an 11-inch impeller, maybe 10 and above. But you start getting down to 9.5, 9 inches, you may still want to trim it as well as put the VFD on.
So we have a couple of other quick questions here.
Yeah.
Do the impellers, or does the, let me rephrase that. Do the impeller diameters deteriorate over time? That's a great question, actually, when you think about it.
Well, if you use our 4900 and it's a nice clean system, the answer is no, but they are going to have some deterioration, or they could, if the water isn't that clean. And probably, unfortunately, especially in the United States, our friends in Europe have very, very clean water, but here there are some systems that would affect that. Is it that drastic? it really depends on the system fluid, I would say. Wouldn't you, Rich?
Yeah, that that you hit the nail on the head. A well-maintained system in terms of the quality of the water or fluid. Let's use the word fluid because it could be a water, like you said, water glycol solution. Does impact the longevity of the pump, not just the pump, but everything else in the system as well.
I will say this. We don't sell a lot of spare part impellers. I don't think that's a big seller at our factory, out of our shop, at least based on the numbers that I've seen. Right, Rich?
Yeah, that's true. And I've run across a couple of jobs over the last few months. I ran across one job where the pump was 40 years old. It was a Taco pump, 40-year-old Taco pump. So under the right, operating, maintaining the characteristics, the cleanliness of the fluid, and maintaining the quality of the fluid, the pumps can last a very long time. So
it's like changing the oil in your car. You got to maintain equipment to keep it running as it should. This product line, our product lines are designed to last at least 20 years, at least. And if it's properly maintained and the system is operational as it should be, read the I&O manuals and what it says there and whatnot. Yeah, it's going to last upwards of that, if not longer.
yeah, and I think the opposite is true. If the system is not well maintained, the fluid is not cleaned and properly, dirt removed and the air removed and stuff, the impeller can be impacted. And we can also have cases, you mentioned it earlier, if we have a net positive suction head or cavitation issue. Sometimes you can have cavitation because you don't have the proper amount of pressure on the inlet side of the pump, but you can't hear it. It might be very, very slight, but that will tend to deteriorate the impeller over time. But like you said, when you consider the thousands and thousands of pumps that we manufacture each year, and the number that require impeller changes is very, very small. So it depends on the system.
I think to add to that, Rich, if you're involved in a project or a system, and maybe there's some deterioration of the impeller or something else, and you call the pump manufacturer, and green and other colors, we're gonna suggest there's probably a system issue first, I think, right, Rich? And not to be quite honest. So anyways, any other questions?
Yeah, we got one more. Let's do one more, and then we'll kind of circle back if we have some more questions. But I kind of like let's see this one. Oh, here, this is kind of cool. It says someone said that impellers usually only need to be replaced if there's a disaster, and that one came from Elizabeth. Yeah, that's true. If you have a disastrous system or some other weird thing that's happening, let's put it this way: we don't design our pumps to pump nuts and bolts and loose things that come through a piping system. So,
no.
Yeah, that's cool. Why don't we move on, Brett, and
All right.
we might circle back and pick up a couple of other questions as they pertain.
And then the impeller spins and accelerates the liquid radially. And by the way, I'm going to get my bouncing ball back. It does not suck or scoop the water. It throws the water. So it rotates in this direction. See these veins here? It does not scoop it or suck it. Pumps don't suck. I apologize for that terminology, but anyways, they do throw the water out the cutwater and out there. So, and the cutwater is what diverts the liquid out through the discharge. And just to reiterate, the impeller eye is the point of lowest pressure inside the pump. Just some educational information here, so you're aware of different types that are out in the industry. You have a center line right here, makes sense, center line, and a tangential. That's that big word that means out here. Tangential discharge. So there's different types out there. Center line has some positives. And this one does too. You know, I'm not trying to throw too many stones here. Weight is evenly distributed, and it's self-venting, means any air that's in the system. Now, obviously, the pumps don't get, they're not an air removal piece of equipment, but it does help. If you think about it, the air doesn't get trapped up here. It's going to find its way out into the pumping system. And all of our end suction pumps are centerline discharge. And I'm sure these folks here, in the old days anyways, before the DOE got involved, probably designed it with the tangential because they had a couple of points higher efficiency. They didn't have as many losses internal in the pump. If you think about it, our water had to get around the corner and out. Theirs just had to go straight out. So anyways, just so you know, centerline tangential, again, a fundamental statement there. Some more components of a base-mounted pump, a centrifugal base-mounted pump. The base, that's one of the components. You know, and ours is a welded 4-channel base. There's other ones out there. It is, I know that the TACO bases are designed to the Hydraulic Institute standard. The Hydraulic Institute is a group of pump manufacturers worldwide that have put standards together to make sure we meet minimum requirements. And this is for all pumps, industrial and whatnot, pressure PD pumps, as well as these basic HVAC pumps. Ours does have a drain pan right here. There's the suction, there's the discharge, casing, volute, wet end, whatever you want to call it. The bearing frame, that's so this is what we call, this pump has 2 shafts. One shaft attaches to the impeller, and then you have the motor shaft. And then they are I'm going to have another drawing that shows you where there's actually a space between them too. But the bearing frame helps support the impeller shaft as it comes out. And we'll talk about that in a little more detail. And then there's the motor right here. You know, it's a pretty standard premium efficiency motor. And then you have a coupler. There's couplers underneath here, and there's a coupler guard. Pump manufacturers, I&O manuals, whatever you call them, I&O manuals, will explain in there that this base needs to be grouted. It needs to be properly aligned, and it needs to be grouted. And there's a whole section in the manuals on that. And you can be surprised if you have an issue with a pump and you call a pump manufacturer or a rep of a pump manufacturer, and they may tell you that it's not warranted anymore. You're running it and it's not grouted. So please beware of that. It's education, right? I like to educate people. The less surprises in life, the better. So there's a whole procedure on how you do that. But nonetheless, that's just filling this cavity up with, in essence, a concrete type of setup. So
here's this is a question. Actually, it's a statement combination question, right in line with what you were just talking about, Brett. And it says, when is it recommended to grout the base? And the answer is always.
I have
always recommend grouting the base.
If the question is recommended, the answer is always. From a practical standpoint, you know, I'm not even going to get into it. I've seen many pumps, smaller ones, without grouting, but I've seen plenty, especially the bigger ones, with grout. I'm sure, Rich, when you were on the other side of the fence, in your specifications, you must have had grouting or follow the I&O manuals of the pump manufacturer and grout the bases, I would suspect.
Yeah, if it had a base, we always required it to be grouted, and it's the sort of the industry standard.
Yep. And most installers, many of our reps would have that capabilities, or you know, could get contractors have it, but many of our reps have a team that could go out and do it, or get involved with a team that could go out and do it as well. But
so here's another question along the lines that this is a great question. Is there any benefit to adding spring isolators to bases after grouting the base, or does grouting the base eliminate the need for spring isolation? So there's actually there are 2 separate topics that are going on here. The main reason for grouting the base is to stiffen the base so that we add rigidity to the base. And that way, when the pump and motor are bolted down, we have a, taking into consideration, like Brett said, the motor shaft, the pump shaft, the coupling, the base, the grout, that's all one unit. Whether or not the unit needs to be physically isolated from the building with an inertia block and springs, that's a separate issue. That does not have anything to do with the stiffening the base so that the pump is properly aligned, so that it doesn't come out of alignment. So isolating from the building, that's a separate discussion, and that you should have that discussion with your acoustical engineer, vibration specialist that wants to minimize the amount of noise and vibration that's transmitted into the structure of the building. Two separate topics.
And this may come up from some folks in some part of the country. And I think, Rich, you've been involved in some. I know I have been in the past. There could be some is it earthquake requirements for pumps or whatnot?
Seismic.
Seismic. I'm sorry, seismic. Well, that's the result of an earthquake, but yeah, they can. You would have to work with your manufacturer's rep or the manufacturer or the design team to make sure that it's properly taken into account for a seismic calc, and maybe get a professional engineer involved in that as well. Here's a kind of a little cutaway. There's the coupler that has the two shafts attached inside of it. There's the bearing frame, a picture of an impeller. You can see the vanes right there as well. The mechanical seal. I'm going to talk about that. Get some as much information as you can. The basic seals that we send out and most pump manufacturers stand out are good for normal type of water and maybe some glycol. But if you start having issues, and I see plenty of specs out there where they insist on maybe tungsten carbide or higher end seals that us pump manufacturers offer, and they just want it on any of their pumps because they don't want to have an issue with it. So the seals is one of the components that you really need to, it's not good when it starts dripping. That's probably the part that wears the fastest on pumps. And again, it still has to do with the system water and the cleanliness and whatnot. But nonetheless, that's probably one of the parts that does need to get replaced at some point in time on that as well. There's the pump shaft. Our bearing frames are very robust, and we actually have what we call a Fushida seal here on the end, because there's an opening here, right? So we have this special seal so dust and grime and grit and whatnot can't get into that cavity. And we have sealed for life bearings as standard. They still have an L10 life way out past 60,000 hours. So you don't need to, you still can get them as a special if you want to lubricate them, but these bearings do not require lubrication as well. And then I would be remiss in not to talk about at least a little bit, touch upon how important it is to align these shafts. And the manuals that the attachments that are available explain that a little bit on the base mounted, and it's within 5 thousandths in 3 directions, horizontal, vertical, and angular. So it's very, very important to do that. I can't stress that enough. The alignment of a pump is critical for its proper operation. And again, our manufacturer's reps can make sure that that's done properly, or I'm sure most contractors get involved with that on a regular basis as well. There's a picture of the Woods Duraflex coupler. Pretty standard. You can get a lot more information on there. Very good for variable speed applications, which is what, 85%, if not more, of our applications nowadays. I do like to at least show this. We call it the old style. Some folks may still use it. This is the Woods SureFlex instead of the Duraflex. Okay, and this is what I've seen this on jobs. We used to use it, but we went to the Duraflex because on variable speed applications, maybe if it's really speeding up and slowing down a lot, these points here would start to grind off, and you'd start to see it on the base. So, you know, if you get involved in an older project, which there's plenty out there, you know, you may be asked that question. I know that some people appreciate being at least told about that. So that's something to consider. The most popular for in the United States anyways still continue to be the end suction pumps, right? Suction and discharge are at 90 degrees, right? I think we've covered most of that. This is what we call the split couple. This is the Taco FI over here. Let me put that on there. So this is the FI. My penmanship with my right hand here isn't that good. And this is the CI. This is the CI. So the difference between the two is it's pretty obvious to some people maybe, but not to everybody, is this one has two shafts, so it's what we call split coupled, and this one is close coupled. So this motor is the impeller shaft. Over here, you have the impeller shaft and the motor shaft, and you have that coupler in between, okay? The performance of the models is the same. So if you got a CI 3007 or an FI 3007 and the impeller is the same, the motor is the same, the output you could expect is the same. So the wet ends are the same. So that's something to make sure you understand there. Most people on the closed couple pumps, maybe for it's going on a base or something like that, you may not see too many, but once you get over 10 horse, 7.5, 10 horse, I would recommend this type over here. You don't have to, you have enough, in order to change the seal on this type of split couple pump, you just have to loosen, you don't have to, none of this has to be, the piping doesn't have to be affected. The motor doesn't have to move, be lifted out of the way. It may have to be loosened and twisted so you have enough room to spacer in there to get that out. But nonetheless, your maintenance is a lot easier. Over here, if you have to get at the seal, you have to take the motor out, and that's that can be a you know, the motors get heavy, right? You know, that's a fact, Jack. They do get heavy. We do sell these up to 60 horse as well as other pump manufacturers because it's a JM style motor, and they sell them up to that. So, but nonetheless, I wouldn't necessarily do too many that size unless it's maybe. Anyways, I digress. Just so you know, I said I was going to talk about seals a little bit. Let me erase. Why did I do that? Oh, I didn't erase that, Rich. You know, sometimes you get out of practice here. Erase all drawings. Here we go. So this is just a cutaway of the seal. This is the type of seal here. Our particular design has a dry shaft design. It prevents corrosion on the shaft, but you can see the components of the seal. Most of us pump manufacturers use a John Crane type of seal. Pretty common out there. You got to be very careful when you change these. If you smudge these up, they're gonna cause some issues for you. So you know, stuff to consider there. I see a lot of people in specifications order a seal with a spare part seal up front because sometimes the pump is used as the startup pump, you know, cleaning, flushing pump or whatever, and maybe the seal might get damaged or whatnot, so you might have to change it right away. So that's something to consider there. But nonetheless, that's just a cutaway of what you see in the seal there. Here's a little closer cutaway. You know, you can kind of see the covers here. There's the impeller, the slip-on shaft seal, and there's your rotating elements right here. There's the pump shaft, the cutaway, and there's your stationary seat. So that does prevent the water from leaking out. And you can order different materials of these. I think our standard one is a Ni-resist, but nonetheless, you can get tungsten carbide, and there's other materials of construction that you can see in our brochures for some of the seal materials. And again, I see some specs out there where that's what they recommend on all of them. So let's talk about different style of pumps, okay? These are called the inline pumps, split or closed coupled. So, you know, that's kind of common technology or statements. So they're inline because the suction and discharge are inline. Even though the motor is this direction, right? The suction and discharge are inline right here. So this is your horizontal, right? The piping is horizontal, and this is your vertical. Excuse me, it's the motor direction that tells you whether it's a vertical inline or a horizontal inline. So it's differentiated by shaft orientation. So over here, this is the Takeo. Here goes my writing again. Oop, let me change that. This is our 1600 right here. You'll notice this one's not green. God forbid. And this is our 1900, but that's because it's probably for an OEM. Some of our original equipment manufacturers get our products and they have special colors that they have. This is our KS model right here, split coupled, and this is our KV model. And again, the wet ends are the same. So the output you can expect from these two would be the same, and these two would be the same. My penmanship is terrible. So the little ones here, they only go up to 200, 250 GPM. A lot of schools, small apartment buildings, you know, smaller commercial projects. It's amazing how many of these are out there. And by the way, these are self-supporting. It's right in the I&O manual, and shame on me, I didn't include it for the horizontal, the little 1600s. But do yourself a favor, never support this motor in the field. Do not support this motor when it's installed. It is designed to be self-supporting. Obviously, this one looks a little different because it's bolted right up. But if you start supporting this and you put a little tension on that, you have a good chance of getting this out of alignment and causing all kinds of issues. So something to be considered there as well. The growing part of our business is the vertical inline pumps, the KV, right? The closed coupled, and the KS, the split coupled pumps. And again, the wet ends are the same. And these go up pretty high. I think we can get a 19-inch impeller way up there in GPM as well, much higher than the base mounted pumps. So something to consider there on bigger projects. There's some other positive reasons why people look at the vertical inlines, and our friends north of the border probably specify those even more than they are in the States. And one of the reasons is no alignment, no alignment issues, okay? It's all bolted up, hard bolted in place. I don't care if it's a split coupled or the closed coupled. So that whole alignment issue goes out of the way. Grouting, there's no grouting there, you know, so things to consider in that regard. And then this KS pump, the split coupled, you can change this seal without moving the motor or affecting the piping. There's a whole video online that shows you how to do it. It's in our instruction sheets as well that you have access to. But so there's another reason that you can do. Maybe start specifying these. And they should take up less space in the mechanical room. They should. It depends on how you pipe it up and whatnot. So stuff to be considered there. And then we do sell a stand that you can have there. I think up to 10 horse or maybe 15. You could probably have these self-supporting, especially the closed coupled ones. But again, that's all spelled out in the instruction sheets as you go there. People ask Rich and I and others, what applications should I use a base mounted pump or a inline pump? You know, the verticals. And really, a big part of our business is the FIs, CI line, and the KV-KS line. And our answers are, it's a difficult question. They're good for all four of them are good for all applications. Heating systems, hot water systems, condenser water systems. It's really personal choice. And maybe your office has always done base mounted pumps. So you always do those. You don't step out of line and try the verticals. And someone else may use verticals. It's the crossover from an application standpoint. It's really a personal choice. Wouldn't you say that, Rich? It's kind of personal choice.
Yeah, I think as you pointed out in the past, the KS KV do go larger than the FICIs.
Yeah,
but
quite a bit larger.
Other than size, it becomes a personal preference.
And I think if I was on your side of the fence, and when I say your side of the fence as a design engineer, installer, whatnot, I would tend to try to convince people to use these verticals over here as much as possible, because of some of the inherent benefits, you know, from a change in the seal, the alignment potentials. If you've lived with some alignment issues, it's a pain, right? It can be a real pain. So something to consider. And then, you know, I think most of us can understand that this model costs a little more than this model because there's more components, right? I mean, it's kind of pretty obvious, but I wouldn't go much higher than a 7.5, just like I said on the set CIs. I think some of my reps break it off at 7.5. I've heard others say 10, but nonetheless, just don't, you know, think of it. Us engineers are supposed to think about the whole project, and really from a maintenance standpoint, you start specifying a KV with 20 horse, 30 horse motor. Sooner or later, someone's going to have to jerry rig that to get that out of there. Over here, they can probably replace it, change that seal without affecting the motor. So these are KV, KSs, 1600, 1900s are inline, split coupled or closed coupled. And again, there's other colors of these out in the industry. We're not the only folks that offer them.
We do have a couple of quick questions, Brett.
Yeah, awesome.
Yeah, so one that just is asked all the time is can the KV pumps be mounted horizontally?
Up to it's in the I think it's up to 10 horse, only up to 10 horse. The KS cannot be mounted horizontally. The KV up to 10 horse can be mounted horizontally. I've seen some of the KVs be mounted up near the ceiling, the smaller ones, but you know, without any support at all. Any others?
Yeah, the other question was, is there a minimum pump speed recommended for seals to be most effective?
We just came across that the other day. Some people say 15, some people say 20% of best efficiency point flow rate. Anything to add to that, Rich?
Well, I think they're asking speed.
Oh.
Is there a minimum pump speed? And I think the answer is generally it's 20 hertz.
Right, 20 hertz.
We don't recommend running the pump at lower than 20 hertz.
And it's not because the pump can't, it's because you need to protect the seals, right? I mean, that's the bottom line. The seals need water or flushing in order to operate correctly or to keep going.
Tay made a comment. I think he's commenting on your motor size for the horizontal mounted pumps. He's saying it's 15 horsepower.
Is it 15?
I think he's
I'm a
right.
little conservative. I will only do it up to 10, but our book says 15. Thanks, Tay.
Tay, thanks a lot. That's good information. Yeah, you can go up to 15 horsepower.
Yeah. And by the way, okay, I'm not going to spend a lot of time on this. We have some other classes that get into the self-sensing, starting them up, and as well as the theory of them and all that. But many pump manufacturers offer pumps now that are called self-sensing. So some folks asked about drives or brought in the drive combination or statements, right? And I mean, that's what 90% of our business nowadays, especially on the KVs, KSs, and FIs, CIs. So a lot of pump manufacturers will supply a drive with the pump, and these are intelligent drives, so they're integrated and whatnot. And again, I don't want to spend a lot of time on this, but I do want to make people aware that they're out there and get more information from your manufacturer's rep or others to understand these even better. This is another product that I would try to specify if I could on projects as well, because I like things to go in smooth and simple and starting up nice and easy. So something to consider there. And I know we offer them not just on vertical pumps, for on our base mounted pumps as well. But again, you can get more information on the self-sensing pumps from our Takeo reps as well. And then some other common styles, not really common that much, are our horizontal split case and vertical split case. I mean, these are very robust pumps. They're the biggest ones that we offer, well, except for our turbines, but nonetheless, you can see how big they go up to. And when we call split case, that means the casing splits right here or in the vertical directions to get at all the components. This is our TA model over here. This is our TC model, top connection model over here. Some bigger ones. So You know, some folks still specify these maybe on bigger projects, but nonetheless, not that common anymore. Not that common. You know, in the old days, real old days, you know, when the slide rule was around, maybe they were a little more robust, but most pump manufacturers have improved their designs of the base mounted and the verticals, so they last just as long as these bad boys here do as well. We also, there are some vertical line shaft turbine pumps out there. All the other pumps that we're talking about need a flooded suction, right? In order to operate correctly. These guys can actually lift the water. So if you have a sump application or whatnot, they can lift the water up. And so Taco does have a vertical turbine offering for HVAC, as well as if you ever have an industrial wastewater municipality type of project, farming, we have a complete line of that. That's a whole different setup. They're actually manufactured in different parts of the United States, not in Cranston, but nonetheless, we do have a vertical turbine. And just to show you how it works, you can see the water goes in here, and then it kind of flows through. It's sucked up through these bowls here and out to the system. So that's how a vertical turbine works in that regard. Here's we were talking about capacities and speed and whatnot, and you could see the vertical inlines go up to roughly 12,000 GPM, right? The end suction, the FIs, go up to just over 4,000 GPM. So there's a big difference there. So obviously, when we talk about applications, bigger jobs, you're going to either look at the verticals or the split cases. So something to consider there. And you can see the horizontal inlines go up to barely up to 300 GPM, just under 300 GPM. So, you know, it depends on your applications and which one you want. You know, and there's obviously the pricing differences between all of them as well. And then your horsepower is here. And for the most part, it's 1760. But, you know, there are options for 1160. And now I'm just talking US. Right, we have other speeds for our folks outside the U.S. as well, and then the 3500s. I try to specify 17 or have folks spend 1760 as much as possible. You know, availability of the motor, price of the motor, lead times, especially nowadays with the lead times issues that we all have out there in life. You know, stick with that, but nonetheless, you can kind of see some of the differences here. And again, I think Rich and I have a special. Taco has a special. If you have 10 KS 600 horse motors, we'll buy you a sandwich or two.
Half a sandwich for 600 horsepower, Brett.
Half a sandwich.
Half a sandwich, and it's a Subway. And
their choice of flavor, though, or type.
Yeah, they can pick anything on the menu as long as it's 6-inch, and we don't throw in the cookies or the drink.
Oh, geez. I might do that. I don't know. We'll see. Anyways, this is kind of a rough layout of the capacities of them as well. So a couple of other things before we finish, and I just want to go over some basic rules of pump piping. All right, I got 5 posted here. There's plenty others, right? And you know, when you start up pumps with a drive and integral drive or whatnot, it's so important to make sure things are, you know, the air is out of the system, the water's flowing correctly and whatnot. But keep suction piping as short as possible. Okay, don't have a long. Keep it as short as possible. Suction pipe diameter should be equal or greater than pump inlet. All right, so try not to, if the pump inlet's 4 inches, don't go from 3-inch pipe up to 4. Have a 4-inch or 6-inch going into that pump. Otherwise, you could create some turbulence. These HVAC hydronic pumps, they like smooth water coming in. They don't like it coming in swirling by any stretch of the amount. Eliminate elbows mounted on or close to the inlet nozzle of the pump. You know, the old saying, 5 to 10 pipe diameters between the pump inlet and an elbow, maybe a long radius elbow. A lot of people nowadays use suction diffusers. That's a piece of equipment that I think every pump manufacturer supplies, and that allows you to have a 90 that mounts right to the suction of the pump. There's straightening vanes in it. You know, keep that in mind. Watch your orientation of elbows on double suction pumps. You want to make sure that's correct. Just to keep the flow going correct into the pump. Otherwise, you can cause turbulence on that as well. Eliminate the potential for air pockets in the suction piping. Air in pumps, I mean, air and dirt are deterrents to pumps, HVAC hydronic pumps. And so if you can eliminate air pockets, ups and downs and whatnot, very, very important. I can't stress that enough in that regard. And then support the piping. The pump cannot support the piping. It's going to put strains on it. We have pictures. You walk into a room and you could tell it. The flexible connector's twisted or whatnot. The pump is not designed to support the piping, so you need those pipe hangers properly mounted to take the strain off the pump casing and stuff like that. Well, I've been talking for a while, Rich. Do we have any other questions right now?
Yeah, we got some great ones. Let's pick one of the newest ones, and we'll kind of work back based on the amount of time we have. So the question came up with an eccentric reducer on the suction. Should it be flat on the top or flat on the bottom?
It's supposed to be. I'm going to say it wrong, I think. In order to get the flow correct, I need to go look at our I&O manuals. I don't want to answer that. Do you remember the answer to that one, Rich? I'm going to screw that up if I answer it.
Tay says flat on the bottom.
Flat on the bottom, so you get the proper flow going in, and you don't get the turbulence. Thank you, Tay. Tay's going to do this presentation.
Yeah, we're gonna recruit Tay to do this presentation next time. Tay, you're in trouble now, man.
I owe him a couple of margaritas when he comes to town.
I know it.
During the summer.
Okay, so here's another great question. In terms of efficiency between vertical inline and end suction, which is better for the same application?
Great question. And it's almost 50-50. Take-o-wise, anyways. I've done I selected 10 pumps on 10 different flow rates and flow and head. Right, you make a selection for a base mounted, and you make a selection for an inline, and it came out 6.4, 5.5, 4.6. So they're very, very close. It depends on the flow and head. Our engineers, our R&D engineers, did a heck of a job when the DOE gave us some mandates on our vertical inlines. I think many folks out there before the DOE got involved, whether that's another whole story about that, but nonetheless, probably said the FIs or the base mounted pumps were more efficient than the vertical inlines, just because of the internals and a little more moving, resistance inside the pump. But our R&D engineers did a hell of a job when they redesigned those pumps, and now it's very close. It's within a point or two, and on some design points, I've seen the vertical a little higher, 1 or 2 points, and other design points I've seen the base mounted a little higher, 1 or 2 points. Almost negligible. When I'm saying 86 compared to 87, 88 compared to 87, there wasn't a big difference. Very rarely was it more than 1 or 2 points between the two. Anything to add to that, Rich, based on your experience?
No, I think that covers it. Here's another great question. Let's see. Do you see issues with heat with pump-mounted VFDs? So we should clarify first. The only VFDs that we allow or that we offer on pumps are the vertical inlines. There you go. The vertical inlines, and I believe we limit that. I'm going to ask Tay to chime in here. I believe we limit that to 60 horsepower. Is that correct?
I'm pretty sure, Rich. And then anything above 60.
Tay says yes. Tay, you're really on top of your game today. Yeah, 60 horsepower. And do we have a problem? No, we have not experienced any overheating of VFDs when they're mounted on the pump. We have not seen any problems with our pump-mounted VFDs. And again, we only offer them on the vertical inlines up to 60 horsepower. Now, perhaps you've seen other manufacturers that have different configurations, and maybe they're having trouble with VFDs overheating, but perhaps they're putting them on larger pumps. I don't know for sure, but we have not experienced any issues with respect to that.
Currently, our base mounted pumps, our FI pumps, the VFD is mounted remotely.
Correct.
It comes with the pump, but it needs to be remounted remotely. Matter of fact, these can be mounted remotely as well if you'd like. When I say these, the two that are on the screen right here.
So here's another question. Do you have any pumps for medium and high temperature hot water systems? And the answer is yes. We do
All
provide pumps for high temperature applications.
I think our pump spec, can I get to the, if I get to the website, go to products. We were at the AHRI show, or some of us were at the AHRI show. I didn't see Tay, but I seen his coworker out there. And suction pumps. I go to the FI performance data. So features. Where the hell is it? Isn't it under performance data? I thought I knew. I thought.
Try applications, Brett.
It's
hot water systems. No, we might have to get back to someone on the actual temperature.
No, I know it's wrong.
It's hidden in there somewhere.
Temperature up to 250 standard.
Standard.
Operating spec. You can see the chart here. It does fall off in accordance with the standards for pressure temperature rating, but nonetheless, when they say high temperature, define high temperature, but nonetheless, our standards up to 250. Anything else?
Let's see. We've got some great. Let's see.
We're already past one.
The person says we have an application for 320 degrees Fahrenheit. Here's what I would recommend: that you contact your local rep.
Yep.
And then we can get together with the rep and we can look at your temperature requirements and make a recommendation. Generally speaking, the temperature requirements will be limited by the seal choices. So, yeah.
See right here, Rich, in our manual it says above 250, a cooled flush is required and is recommended for temperatures above 225. So again, I think that was a great answer. Get in touch with your manufacturer's rep for specials like that.
Yeah, because we do have lots of information to provide as specials. So.
Yep.
Oh, wait a minute. We've got a comment here. I beg to differ with Tay on the eccentric. Oh, I'm not going to go through that because we need to spend a little more time going through that. Well, actually, at this point here, we're a little bit past 1 o'clock.
Yep.
Do you have, let's see, does anybody have any last question? Somebody want to type in the last question of the day? So do we give any prizes away, Brett, for the last question of the day? I don't know. I don't think we do we?
Yeah, they can get a copy of the recording tomorrow in 24 hours.
That's right. I forgot to mention that.
They'll be the first one.
So in roughly 24 hours from now, you can get a copy of today's recording, and you can also get an email. We'll give you a link for downloading a certificate so you can get your 1 hour professional development hour. So I think, Brett, do you want to say a few words before I sign off?
No, yeah, thank you, everybody. And if you want to call Tay direct, there's his phone number right there. Proctor Sales up in Anchorage, Alaska. Thank you, everybody. Great questions. Appreciate your time. Thanks for listening. Rich, take it away.
Well, we want to again say thank you so much for everyone participating in today's TACO. Today it is TACO Tuesday. But by the way, did you know what else is unusual about today, Brett? It's the date. It's 2/22/2022.
Wow.
And I read somewhere that this only occurs, this kind of number lineup only occurs once every so many years. So it'll be interesting.
I think today's actually George Washington's birthday.
Is it George's birthday?
I'm pretty sure the 22nd, but.
Is it true that George had wooden teeth? I don't know if that's true or not.
I don't think that's true.
I have no idea.
Yeah. Hell yeah.
Well, in any event, we want to say again one more time, thank you so much for participating in today's presentation. We are going to sign off in a few seconds here. Hope to see you on what night is it this week, Brett?
Takeo After Dark commercial Thursday night, 7 o'clock.
Thursday night at 7 o'clock. Yes, that's East Coast time. So if you want to join us for Takeo After Dark, we start precisely at 7 p.m. And our formal presentation lasts just about an hour, but we do stay on afterwards. And sometimes we did one time, we stayed till about 9:30, about an hour and a half after our formal presentation. So yeah, it's lots of fun, and hopefully we'll.
So Rich, a couple Carrie typed in ambigram as the date and planodrome.
Palindrome and ambigram.
Not that I know what that means.
I have no idea what those words mean. I can only do 1 or 2 syllable words.
Yeah, I know.
Kay is very impressive today. It's like he's the man of the hour.
Yeah. All right, guys.
Go up and visit him in Alaska.
Thanks, everybody.
Thanks a lot. Signing off. Take care now.
Well, hello, friends, and welcome back to Takeo Tuesdays. It's really awesome to be back live on the air, so to speak, or live on the interweb, so to speak. We're really happy to have you all with us. It's been a few weeks as we got 2022. I'm still writing 2021 on checks. I guess that's to be expected. But really good to be back here in 2022 to share these Tuesdays with you and to get the rest of our online training program off on the right foot. So we're really excited about today. We're really excited about this week. We're going to be tomorrow night. We're going to be bringing back Takeo After Dark, which is going to be really exciting. And on Thursdays we'll be doing a commercial Takeo After Dark as well. So this is going to be a lot of fun for the coming year. Hope everything's going great with you folks out there and wherever you happen to be in the world. And let's get this thing started. First things first, just want to make sure everybody can hear me. I think you can because Jeff House mentioned who uses check. So I know my voice is getting to you. So that's awesome. A couple of things, just some housekeeping things. First off, if you go to your questions chat box on your control panel, please type in a hi, hello, how are you? Just so I know, A, you can hear me, and B, you know how to ask questions, because that's going to be how you ask questions. Questions are going to be wicked important today as we go through estimating fuel consumption in hydronics. So good, everybody can hear me. Folks out there have figured out how to ask questions. That is good, that's good. So again, there's no particular, we don't, one of the things with Takeo, we don't say, save your questions till the end, because that's kind of lame. Ask your questions as they come up, and we'll try to answer them as best we can. What we'll do is we'll take every few slides, we'll take a little break, and look at the questions, answer a few, and then move on. And then I'll stay on as long as you folks want after we're done at around 1 to answer as many questions you have about this material, and really at that point, anything you want to talk about when it comes to residential hydronics. So that's important there. So make sure everybody seems to be pretty good at that. That's excellent. There's also a couple of handouts. You should see a section in your on your control panel for handouts. You can download those. One is a heat loss factor guide for you with all the different heat loss calculations and formulas and information that you might need. And the other is a correction factor for degree days, which will come in handy in just a little bit. So with that out of the way, let's get this show started, shall we? Again, well, my name's John Barba, just in case if you're a first timer and we don't know one another. Pleased to make your acquaintance, and thank you again for being with us. Today's topic is estimating fuel consumption in hydronics. There's a lot of ways to do this, and there are a lot of reasons to do this. Some of them are really good. Some of those reasons are really good. Some of those reasons can get you into trouble. So what we hope to do is just to be able to navigate you through that mathematical process and share with you what might be the best modes for dealing with that, for using that information to help you and your customers decide the best route to take when it comes to updating or replacing some of their equipment. So again, the question we want to ask is, why would you want to estimate fuel consumption? I'm going to throw that out there to you folks. Why do you think? Type in your answers here in the chat section. Why would you want to estimate fuel consumption for your customers? What would your goal be? What's your reason? So type in a little answer there. I'm interested to hear what you folks out there are thinking. Yeah, cost, to provide costs is always a good, that's a start. Yeah, that's a start. Show them savings with higher efficiency equipment, says Brian. Absolutely. Equipment sizing, energy rebates. Okay, all good stuff. Make decisions. Excellent stuff. Now let's kind of compare system types. Now that might be my favorite one so far, but they're all pretty good. But just the question people always ask whenever you talk about whenever they're considering upgrading their equipment is, well, what's my payback? And to me, that's the worst question they could ask. And what's worse is trying to answer it. Okay. A boiler's not going to pay anybody back unless it gets a part-time job. Okay, we got to understand that right away. The payback is the wrong question. All right, it's the wrong question, and that question shows up in a lot of different ways. What's my payback? There is no payback here to speak of. The other way they'll ask that same question is, well, when will this thing pay for itself? You know, when it gets a bank account and a job, right? It doesn't work that way. It does not work that way. The question is, that's the way the question is stated, but it's not the question that you need to answer, and it's not the question really they're asking. What you have to understand is we're talking about an appliance. It's not an investment. I've heard people say, oh yes, your boiler is an investment. I've had people unfollow me on Twitter because I said this boiler upgrade is not an investment. It's not an investment because it doesn't increase your net wealth. You can't write it off on your taxes. It's not an investment. It's an appliance. It's home maintenance. It's things you need to do. So it's an appliance. It's no more of an investment than a refrigerator or a toaster oven if you think about it. It is an important one. It keeps you warm in the winter. It makes hot water for you. That's important stuff. The thing is, we want to put as efficient of an appliance in there as we possibly can. All right, so that's a way to look at it. To me, that's the right way to look at it, because ultimately people look at it as an investment, but in reality, it's a pig, right? You're putting a pig in the basement, okay? It eats fuel and it poops heat, okay? That may be the most graphic way to put it. That's what it does. It's a pig, all right? What we want is a fuel efficient pig, all right? If you're thinking about that, we want to put that pig on a high fiber, low fat diet so it gives you the most return for your dollar. That may be the better way of looking at it, I think. It's depending upon your customer, that might not be the best analogy, but between us friends, to me, that's the most accurate way of looking at a boiler. All right. It's not going to make somebody richer. It's not going to pay them back and then they're going to start making money on the thing. That's not how it works. It's an appliance. You make a deal with this appliance. Okay. You give it money, it keeps you from freezing to death. That's the deal. Okay. That's what it does. And as long as we understand that, what we're trying to answer, the question we're trying to answer is an upgraded boiler system worth it at this time? If there's I think what we'll find out here is if there's a perfectly functional system that's of good efficiency, that has a lot of life left in it, upgrading to a higher efficiency system may not be quote unquote worth it at this time. The best way to use this information that we're going to share with you, I believe, is if it is now time to replace the system, what is a better long-term decision? Is it better to choose a less expensive upfront, lower efficiency system, or a more efficient, more expensive upfront, higher efficient system? That's what we're trying to do. We're trying to show the relative costs of these two particular options ahead of the game, so the customer can make the best decision for themselves. Let me know if that makes sense to you. Again, I've had a lot of people get really mad at me of saying, well, it's not an investment, it's an appliance. Let me know if that makes sense to you. I think it's a kind of a different way of looking at it, but I think it's also more realistic, again, in my opinion. And your opinions really are what matters for your businesses, but just let me know if that makes sense to you. So why do we go through this process? Of course, demonstrate the value of upgrades. All right. Again, we got something like this in the basement. Okay, there's an upgrade to be had here. Okay, there's some savings to be had here. That thing served beyond a good life. It's time for that boiler to rest. Now it's just a matter of what are we going to replace it with. All righty. It's also to compare options. Do we choose the fountain of youth or the fountain of bacon? I know which way I would go, but you have to make a choice, and you have to help your customer make the best choice for them. All right, and for them, sometimes the best choice might just be a standard efficiency boiler. And here's the other thing. We tend to try to predict what the future will be with some of these things. And I think that's a mistake. Don't look ahead, because you're not Nostradamus, okay? You don't have a crystal ball, and you can't travel ahead in time. You have to look back and say, if you had this equipment last year, here's what you would have spent, because you don't know what they're going to do. One of the things we have found is when people get new higher efficiency systems installed, what do they tend to do? Instead of keeping the thermostat at 68, maybe they bump it up to 70 or 72. Maybe they keep it a little warmer in the house, and that impacts the potential savings. And if you get into the prediction business and you're at all wrong, depending upon the customer, they may be on the phone with you and saying, hey, you owe me something here. This isn't as efficient as you said it was going to be. What are you going to do for me? So always compare backwards. It's risky business getting into the prediction game. In my opinion, you do what you think is best, but that would be the best advice I could give you. So as we start down this process, there's a few things that obviously we need to know. We need a good starting point. Many of you are probably already on board with this, but for those who aren't, we want to all start at the same spot. So stuff we need to know. First, you got to do heat loss. That's why I included the heat loss program, the heat loss guidebook in your handouts, okay? It's manual. This is an IBR manual heat loss, and it's very effective. It's very simple to do, but all of the formulas and all of the data that you need to conduct one manually is in that handout. So you got to know the heat loss, and figuring 25 or 35 BTUs a square foot isn't a heat loss, it's a guess. All right. So have as good of an idea of heat loss on that house as you possibly can. Again, guessing is one thing, but guessing is like a hand grenade. If you're close, best to have a reasonably accurate heat loss calculation for that structure for any of this to matter. Okay, so got to do a heat loss. Also, it's good to know the BTUH content of different types of fuels, depending upon the fuels that you're using. Number 2, fuel oil, 138,500 BTUs per gallon, natural gas, LP, and electric, okay, depending upon what you're working with. So it's good to have that information available, because you're going to need it to do the math, and you're going to, if you love math, you're going to love the formula for this one. So you have to have the heat load. All right, you have to have a reasonably accurate heat load, and you need to know the BTU content of the fuel that you're using. All right. Next, more stuff we need to know. We have to have an understanding of what AFUE is, annual fuel utilization efficiency. It's a number, okay? It's a number, and it comes from the U.S. Department of Energy. And what does it mean? Well, their definition, the DOE's definition, is as follows. It's the measure of seasonal or annual efficiency of a furnace or boiler. It takes into account the cyclic on-off operation and associated energy losses of the heating unit as it responds to changes in the load, which in turn is affected by changes in weather and occupant controls. Okay, good enough. That works for me. That works for me. We need to know that number, and when we use that number, we will express it as a decimal point. So as a decimal. So we will we'll keep that in mind. All right. Next, more stuff we need to know. I love this one. Well, heating season, we have to define heating season. And what we're going to do for our example here, and if you're in Alaska or someplace, it may be different. If you're in South Carolina or North Carolina, it might be different. What we're going to show here, what we're going to define as the heating season is October 1st through April 30th. That's when we know we're going to be running the heating equipment, differing amounts of time during the day, but that's typically what we would call the heating season, and we'll call that 7 months worth of heating season. Also, heating season runtime. Now, this comes from the Gas Appliance Manufacturers Association, and for the cold weather parts of the US and Canada, we're looking at about 2,500 hours. Now, you get into some areas where you get up into 3,000 hours. That's how many hours over the course of the heating season that the equipment is actually on. All right, the equipment's on. You'll get in, interestingly, if we identify the heating season as October 1st or April 30th, there are parts on the West Coast, like from Northern California into Oregon, where that heating season is, the runtime is actually estimated at 3,000 to 3,500 hours, but it doesn't get that cold. So the heat law says it doesn't get that cold, but the amount of time it actually has to run is a little bit longer than it would be here in say, I'm in New Hampshire. New Hampshire is about 2,000 to 2,500 hours. It gets colder here, but the heating season is a little bit more compressed, so to speak. So roughly 3.5 months using 2,500 hours as a constant. All right, and that's the number we're going to use for our application today, 2,500 hours. And then lastly, this one's my favorite, degree day. I was in this business for so long and really never fully understood the definition of degree day. Not entirely sure I do yet at this point, but I can tell you what it means. I couldn't tell you the why, but I could tell you what it means. It's the estimated average outdoor temperature for the winter. All right, but it's the difference between the difference between the average outdoor temperature and 65 degrees over a 24-hour period. All right, it's the difference between what would be the average outdoor temperature over the course of a day and 65 degrees. 65 degrees is a baseline, and that you can move that if you want to. But what the degree day, people who came up with degree day say is below 65, you might want to turn the heat on. Maybe you don't, but we have to start somewhere. And that's what we're talking about, 65 degrees. So here's an example. Let's say the daily high is 40 degrees and the daily low is 20. So the mean there is 30. Okay, so it's 30 degrees. That's your average daily temperature. 65 minus 30, that gives you 35 degree days in that 124-hour period. So if that makes any sense at all, you got 35 degree days in one day. Okay, that works as long as we understand what that is. The why is, we're using it as a calculator here in this case, and you'll see how accurate it is. It does work out to be fairly accurate. So that's 35 degree days. Question came in, do we have to adjust running hours for indirect water heaters? We're going to get into that a little bit. You're going to see how that impacts your consumption, but on the big picture, not really. There's not a math function that I know of anyway that'll allow you to do that. But you're going to see how we're going to factor that in, Alexander. So I hope that helps. All right. All righty. Let us continue. Now, we have to start with a typical house, and this is a typical house that I called home for many, many years. No longer, but I called it home. It's in Prior Lake, Minnesota, all of 900 feet above sea level. 900 feet above sea level, Prior Lake, Minnesota. In Prior Lake, Minnesota, the outdoor design temperature, according to ASHRAE, is minus 12. Does it get colder than minus 12 there? Oh, yes, it does. Not that often, but it does. So our guidelines here are a 12 degree outdoor temperature, minus 12 degree outdoor design temperature, 70 degree indoor temperature for our heat loss calculations. And there you see the house right there on Franklin Circle with the little football field and track backing up against it. The house itself was approximately 2,400 square feet. I got a quickie for you. Without doing the math, what do you think that heat loss would be? House was built in 1978, 2x6 construction. Those windows you're looking at were upgraded in I'd say the mid 90s. But other than that, there's nothing fancy about it. 2,400 square feet. Take a wild guess what you think the heat loss is. I'm curious. We got Zach saying 72,000 BTUs. All right, there's a guess. We got 84 to 94, 85, 72, 73. All right, 5 ton. You would yell at us for guessing? Yes, I would. All right, very good. We've got 45,000 as a low and 120,000 as a high. That's kind of a range, man. That is kind of a range. Let's see what we came up with. Well, here we go. It's heated with a 95% ModCon boiler, as you're looking at there. It was an NTI, and it's a hybrid system. We have an air handler for upstairs, panel radiators and radiant floor heating in the lower level. All right. And Here it is, the calculated heating load, 44,600 BTUs. Interesting, huh? Interesting. I was shocked when I did the math like 3 times and it came up with that 44,600 BTUs, and that's an accurate number. That is an accurate number. So it's interesting how when you really do the math, the BTU load actually can be surprising. It can be surprisingly low. This is a 2,400 square foot house in Minnesota when it was 12 with a minus 12 outdoor temperature, 44,600 BTUs. So let's get into estimating fuel consumption using degree days. All right, here's your math formula. I'll give you a chance to write that down. And also, this is being recorded. You will get an email tomorrow with a link to the recording as well as your certificate of attendance. So you'll get that. So if you're taking notes, which I think is a good idea, you can write this thing down now, but you'll also be getting a recording of this tomorrow. So EFU is estimated fuel usage. The top line, the numerator, is the BTU heating load times 24 hours in a day, times degree day, times something called the correction factor. And again, that second handout will show you the correction factor. So heating load times 24 times degree days times correction factor, divided by our denominator, AFUE, stated as a decimal, okay, times Q, in this case, Q, okay, DD is degree days. There's your correction factor table right there for CF. That's your correction factor. Again, that's in your downloads. AFUE stated as a decimal. Q is the BTU content of the fuel per unit. So again, that 138,500 BTUs per gallon of number 2 fuel oil, 100,000 BTUs per therm of gas, etc. So that's what Q is. And then DTD is your design temperature difference. In our example, we had 70 degrees indoors, minus 12 outdoors. That's a design temperature difference of 82 degrees, okay? So heating load times 24 times your degree days times the correction factor is shown here. AFUE is a decimal times Q, the BTU content of the fuel, times design temperature difference. So get your calculators out. This is going to be fun, all right? So where do we get these numbers? Now that's the other interesting part. Well, in the heat loss handout, we list outdoor design temperatures followed by degree days. Anytime you see a slash with a number, that number after the slash is the estimated degree days for a given area. All right, for a given area. So in this case, we're looking at Minnesota. There's Faribault, Fergus Falls, International Falls, Minneapolis, St. Paul. There's your minus 12 and 8,250. That's the quote unquote normal degree days for an average year. Some years it's higher, some years it's lower, but that's what they consider average. Those are your average degree days. All right. So you can get rough information there. Another great place to get degree days is this website, degreedays.net, www.degreedays.net. And you actually have the ability to dial in your degree days to the neighborhood for a given time frame. You get to select the time frame you want. Now, when we do this, I'm going back in time to a really weird winter in Minnesota, so you kind of get an idea. It's going to be very interesting to check this out. All right, here's the website, Degree Days, degreedays.net. So what you would do is first type in your weather station. So I typed in Prior Lake, Minnesota, and you can do a station search, and you actually get into these weather geeks that report this stuff because they like to. Now, airports tend to be pretty reliable. When you start getting out into the real world, things get a little dicey. But they may not be as reliable. But there are some that are verified as more reliable than others. Pick your degreeing day type, heating and cooling, your temperature units, your base temperature, okay, which in this case is 65. You can change it, and then pick your breakdown for monthly, weekly, daily, average, and then your time period covered, and click degree day, and you can start generating your start generating your costs, or you start generating your degree day rather. All right. So in this case, I typed in I typed in our weather station, or what our idea, what it was, Prior Lake, Minnesota. Clicked on station search, and right here you have the airport. okay, Minneapolis, St. Paul International Airport. But as you look down, you can get into different areas. You can get into neighborhoods, all right, different neighborhoods that might be a little bit more accurate for that particular territory. So as we continue, ultimately, once you pick all of your parameters, you'll get this report. So what I did was I chose, this goes back to the winter of 2011, 2012, which, as I said, was a weird winter in Minnesota. We were playing golf in February, all right? We played golf in February that year. That's how weird it was. It was a weird winter. So this gives you the degree days per month, starting on, let's see, 10, 10, 1, 11, so that is October 1st, 2011, and it goes all the way through September 1st, 2012. So it's a full year's worth of degree days. What we're going to be concerned about is the winter, okay? October 1st through the end of April, all right? So that area that's squared off there. And we add up all the degree days and we come up with 5,833 degree days. Now, if you remember back to what we showed you earlier from the IBR chart, the average winter was 8,250 degree days. So this was a pretty mild winter, right? This was a pretty mild winter by comparison for that part of the country. So what do we do with this number? Well, now that we have the number, we can start to fill in the blank. So again, October 2010 through April 11th. In this case, I'm sorry, we had 5,000, yeah, this was 11 through the 12th, so 5,833 degree days. We go back a year earlier, okay, 2010 through April of 2011, you'll see that that was a much colder winter, 8,021, a little bit more of a normal winter, October, from October 2010 through April 2011. That was more normal. The following year was quite a bit lower. Just so you see how this can differ from year to year, which is why you don't want to get into the prediction business, okay? That's why you don't want to predict. So let's fill in the blanks. I just want to do a quick status check. How are we doing out there, folks? Pace okay? Are we going too fast, too slow? Is this useful? Give me a little bit of feedback so I know you're still with me. So let's see what you have here. So doing good, says Adam. Great. Okay. Good. Excellent. That's from James. Just want to make sure everybody's on the same page and we're cruising along at a good pace, not too slow or too fast. All right. Excellent. Good. So let's fill in the blanks. Let's start doing some math here. Okay. So there's our formula. Let's fill in what we know. What do we know? Well, we know a lot. We know the heating load, 44,600 BTUs, 24 hours in a day. That doesn't change. 5,833 degree days. And if we go over to our C1 chart, okay, so this is just to define the C1 chart. It's apply the correction factors below to degree days to provide a more accurate estimate of the actual heating needs of a residence. Okay, so this turns this into more of a residential focus. You turn the thermostat up, you turn it down, you're in, you're out. Some rooms, you have zones, some are set high, some are set low. It's just a correction factor. So at 5,833 BTUs, okay, we could put in a correction factor. Looks like about 0.605 correction factor. So we've got the numerator. All set. Let's fill in the blanks for the denominator. It was 95% AFUE, so 0.95, 100,000 BTUs per therm. 82 degree design temperature difference. Now we have some fun and we come up with some really big numbers, okay? So what we have here is 3,777,404,136 divided by 7,790,000. Okay, what does that mean in terms of math? Well, let's do it up. And we're going to come up with just under 485 therms, 484.9 therms. The number is going to give you the units of fuel used. It's going to give you the units of fuel used. So 484.9 therms is what we're estimating for the year. And at that time, we paid 75.5 cents per therm. All right, 75.5 cents per therm. Our estimated cost, $366.10. Let me ask you, does that sound high? Does that sound low? Does that sound crazy? All right. What do you think? Is that accurate? Is it nuts? $366 to heat a house in Minnesota. We got very low, we got really low, we got crazy low. Not accurate at all. There we go. It's cheap, about right for the date. Low, I live in New York. Well, there you go. Let's see well, how do we do this? Well, let's compare it to what the numbers really were. Okay. Let's see what the numbers really were, because this is why you look back, guys. This is why you look back. Here's my gas bill for the same time period. 584 therms, 584 therms at 75.5 cents a therm. The actual bill was $437.77. So it's close. It was close, right? You missed it by that much, as Don Adams would say. Why the difference? Well, we forgot the DHW. Going back to what we said earlier, we forgot the DHW. All right. We forgot to factor in or basically take out the cost for DHW, because that same system made the domestic hot water. It had a flat plate heat exchanger. It acted as an instantaneous or slash tankless type water heater. Had a little flat plate heat exchanger, a diverting valve. So when we needed hot water, boom, we turned off the heat, we made hot water, everybody was happy. And it made we had 6 people living in that house, 2 of them teenage girls. We used a lot of hot water. You're going to see how efficient that thing actually was. So we forgot about the DHW. How do we factor that in? Well, let's go back to some summer months, okay? And we can get an idea of, like, August, $19.69, July, $20.97, June, $20.79, et cetera, et cetera. And it's fairly consistent, all right, that it's right around $20. So let's say, okay, we'll call it $20 a month. $20 a month over 7 months, that's $140. All right, that's $140. We can simply take out of that actual cost. So what did it really cost to heat that house? $437.77 for that winter, minus $140. It actually cost us less than $300 to heat that house. Now, let me ask you that. Does that sound crazy to you? Because that's the actual number. That's the real number, taking out domestic hot water. All right. Let me see if that sounds crazy to you. Yeah. Bill says it's correct for the equipment. Math doesn't lie. Absolutely. Absolutely. So interesting, huh? Isn't that kind of interesting? So the actual cost was less than $300 to heat that house for the year. Yeah, Gene says his is more than that a month. I'll tell you what. What was the temperature you set the thermostat? Yeah, that's a good question, Bill. We left it at 68 all the time. So that's going to change the calculations just a tad, but 68 was fine. 68 was absolutely fine in that house. The panel radiators downstairs and the radiant floor were perfect for downstairs, and upstairs was fine too. So 68 we kept that at 68. So that does impact that number a little bit, but that's the difference between but we estimated it at 70. So it still didn't, we still estimated it at higher than it actually was. So very good. All right, double pane. Yeah, I said the windows were double pane. They were installed in the mid 90s. I'm going to say early to mid 90s, updated. So yeah, standard double pane windows. There's nothing fancy about them. So cool, man. Interesting stuff. Interesting stuff. So in this example, that's what you would do with this. I mean, you could compare it to the old system, which we had a very, very old GE furnace that was original equipment from 1978. We compared it, compared the two, and we were much, much lower. Was it life-changing money savings? No, but it was lower. It was less. We had to change the old furnace because it was dead. Okay, we had to change that, and we had to put in something. Would a standard efficiency furnace been less expensive and better than the old clunker? Absolutely. Would we be paying more to heat the house for the heating season than this? Absolutely. But we'd also have a separate hot water tank too, which again changes the equation just a little. It's hard to look at this and say that's a bad deal, because this was a very, very good upgrade for the home. All right. So what do you do with this number? As we said, compare backwards. Here's what you would have spent last year if you had this equipment. So what did you spend last year with the old equipment? Here's what you could have spent last year if you had the new equipment last year. You can't predict the future. Don't try to predict the future. All right. You just got to move forward. Okay. So what did you spend last year with your old equipment? Here's what you would have spent last year with if you had this equipment in it. And then you can compare the two, standard efficiency versus high efficiency. So again, that to me is the best way to do it. If you try to predict what they're going to be spending next year, you really can't. And if they ask you to, you say, well, it's impossible for me to say because we can't predict the weather. We don't know if you're going to have a harsh winter or a mild winter. I don't know where you're going to be setting the thermostat or what other factors that might be involved. The best I can do, and the only accurate and honest thing I can do for you, is to compare the past old equipment versus updated equipment. I think that's the only logical and ethical thing you can do. Otherwise, you could be over promising and under delivering, even if that's what they want. You don't necessarily give them that. Again, then people if they start calculating the payback, the number that they're trying to get to, here's the number they're trying to get to when they start talking about payback or pay for itself, that sort of thing. At what point does the fuel savings between a standard efficiency replacement and a high efficiency replacement, at what point does the difference in cost between those two offset the increased price of the high efficiency system? Now, for that, you also have to factor in, if you're going with ECM circulators, you have to factor in the annual savings of electricity as well, which again, it's a pretty standard formula, but you can certainly do that using that 2,500 hours. And that may wind up being, depending upon your kilowatt rate, could be anywhere from 28 to 40 bucks a year per circulator. So if you got 3 or 4 circulators, okay, let's say 30 bucks, 3 circulators, that's another $90 per year that you're saving. So you factor all of that in. Is it a 2-year quote unquote offset? Is it a 5-year offset? Is it a 10-year offset? That's arithmetic, and they're going to have to figure out what's the best option for them. It's going to depend on how long they plan on staying in the house. What kind of if they're planning to sell the house, do they want to show that they have the best and latest equipment in there? Do they want to just reduce their carbon footprint? That's another reasonable way of looking at it. So again, it's going to depend on what the customer's looking for. All right, now again, if we were to compare this to a standard efficiency boiler, we kind of talked about doing that. Compare the whole thing to a standard efficiency boiler. So we have all of the same information in, but let's put in an 83% efficient boiler compared to the 95%, 83. And you can do this math with any number that you want, but let's say standard efficiency, 83% cast iron boiler. And we're going to look at the numbers here a little bit, and the numbers might be surprising. Okay, that's 555 therms. So we're talking 419 versus 366. So that's 53 bucks for the year. Okay, is that gonna move the needle? Yeah, if you factor in rebates and things like that, that's the legitimate difference. Okay, that's the legitimate difference. So 53 bucks for the year. If it was and that's for a below average year. An average year, if you considered that 8,250 degree days, you're looking at about $80 per year difference. So how does that factor in? Those are things you want to look at. Be prepared to offer that side of the equation as well. All righty, other things to consider when they're looking at their old boiler. Was their old boiler sized properly? Probably not. Probably not. That's going to skew numbers. Were the old circulators oversized? What we're doing here, this number doesn't take into account a lot of other things, a lot of other factors that lead to economy of operation, that lead to efficiency. Oversized circulators. If you're over pumping a system, that's going to skew your number. That's going to skew your past numbers as well. And there's really no way of taking that into account, because if you oversize your circulators, you're getting more flow than you need all year long. As it gets colder out, or as it gets warmer out, you're getting less and less efficient, as it gets warmer out because you're short cycling that boiler like crazy. You can even short cycle your boiler like crazy with oversized circulators if you even in the colder conditions. That's going to change this equation. Then there's really no way to factor that in other than inferring. Okay, so even if you put in a new system and oversize the circulators, you're changing the equation with no way to quantify that. That's why, we talk about delta T circulators because they minimize that short cycling and minimize that oversizing of circulator impact. Delta T circulators do to a degree, even if you hit that little magic button and believe that it sizes itself, which it doesn't. You still have concerns there. They'll use less electricity, but how do they operate within the confines of the system? That's why we have more classes than just this one on how to size circulators and how to create an efficient system. So is the old boiler sized properly? How oversized are the circulators? Okay, 3-speed circulators set to speed 3, guarantee you way oversized in almost every application. That's just the way it is. So you have to kind of figure out that part of the equation. Again, hard to quantify, but it does impact efficiency and it does impact fuel consumption. Again, the higher the heating load too, the bigger the difference. 44,600. That surprised a lot of you folks. It surprised me when I did the math, but that's exactly what it was. All right. So bigger structures, higher heating loads, the differences are going to be an awful lot bigger. All right. And the other thing too is what are the other benefits to a new boiler? The other benefits besides financial to compare a standard efficiency boiler and a high efficiency boiler, there's a lot of other benefits here, a lot of other differences. Space, that thing's up on the wall, everything's up on the wall. You have a little bit more floor space, okay, in the mechanical room, which can be used for whatever. All right. In my structure, we had my house, there was also our laundry room, and it ultimately became my office. Okay, if you remember the old webinars we used to do when I was in Minnesota, I had the boiler right behind me because my wife said I could have my office in the basement. She could shut the door, locked it from the outside. I'm not quite sure why that was, but anyway, so there's benefits to space, there's benefits to noise. Okay, there's benefits to having a boiler that makes that, with that heat exchanger. I didn't need a hot water tank, so again, that was space that worked for me as well. Sealed combustion, a little bit safer than standard combustion, so I was a little less worried about carbon monoxide. So there's a lot of other benefits to consider to the high efficiency option. The other side, of course, is maintenance is now a way of life. Okay, it's not like that old cast iron boiler that you really didn't have to do much to. Annual maintenance on a modulating condensing boiler is a must. Okay, you've got to treat the water. That's a must as well. So there's other factors that come into this besides just the numbers we're sharing with you here. This is part of the equation, but there's a lot more to it. Okay, so those are all different things to consider. So with that, let's throw it out there for more questions. There's a whole bunch of them here. Would you look? Here's one from Jeff. Would you look at the average of the last 3 years to account for mild and cold winters? I think the more information you have, Jeff, absolutely, because compare. I think if you just want to compare 1 year to 1 year, that's a start. Okay, but if you want to compare, do a 3-year analysis, sure, that can certainly change the numbers a little bit, because in this case, standard efficiency versus high efficiency on just one abnormally warm year paints an unrealistically, non-rosy scenario, I guess. A really severe winter would give you a rosier scenario. So yeah, I think absolutely, Jeff, that's a really good point. If the previous year was unusually mild, go back to a 3-year analysis, and then you can compare, different types of winters. I think that's a great idea. Can you just use the percentage difference in efficiencies and tell them you can save 25% on fuel costs? I suppose, Bill. Yeah, I mean, that again, you're predicting. Okay, that's just me. I'm not a predictor. I don't like to predict stuff I don't know. Predicting the outcome of football games is about as much as I'm willing to do. Because again, if you predict that and something weird happens, they're your customers, and you can do that. For me, anything I can do math wise to give me some solid ground to stand on, I feel better. But that's me. Okay, I tend to work that way because let me tell you something. This entire presentation came out with from something that happened to me in 1989. All right, when I was working for my dad, and I was a customer asked for a quote on a new boiler. All right, he had a boiler that was installed. It was an oil-fired boiler that was installed during the height of Beatlemania. Okay, 1964. This was 1988. So it was or 1980, about 25 years old. Okay, so did it still have life left in it? Yeah, if you think a cast iron boiler should last 40, 50 years, yeah, it still had some life in it. But he wanted to know about, how much money he would save, and I didn't know how to do the math back then. So I did an efficiency comparison, and the numbers didn't come out all that great. Okay, and he looked at me and said, "Well, I'd be better off investing my money in a passbook account. If you remember what those were back in a savings account. This is really just a waste of my time." And being 29 years old and not really knowing the math like I should have, all I could go is, yeah. So. And that bothered me for a lot of years until I was able to get into this level of math. And we could have shown him something, but again, he had a boiler that 25 years, maybe you still consider that a baby. All right. So it may not have made sense to him, other than the fact that, the maintenance that he had been doing over the years was not really that great. And we had to fix a few things. So you factor in, potential maintenance costs of the old boiler. Do we want to get this thing to limp through another couple of years, or do we want to take care of it? Do we want to take care of it right now? Those are other factors that you take into. Okay. So now that high efficient boilers have been around 20 plus years, how well will this formula work on today's boilers that are both 95% efficient? Well, again, 95% efficient, if it's been 20 years ago, 95% efficient today, it's the same kind of, it's 95 is 95, right? I think, Jeff, at this point, what you're looking at is how much longer is that 95? I remember when the high efficient boilers first came out, we were talking about a 12 to 15 or 16 year lifespan for these things because of the heat exchangers. People said, why would I put that in? I'll put in a cast iron boiler to last 40 years. Fair question. At some point, that old boiler is going to need to go. I mean, we're getting into that cycle of having to replace 20-year-old ModCon boilers. If they're still fine, if the heat exchanger is still fine, sure, there's no reason to change them. If it's operating fine, there's very minimal maintenance, no reason to change them. If there's more ongoing maintenance, then there might be a reason to change them. At that point, it's not a performance thing, it's an age thing and a maintenance thing, in my opinion, anyway. All righty. Very good. Dan says comfort due to modulation versus on-off flame cycling. I think that's another example of a benefit of an upgraded equipment. If your numbers are removing a 70% boiler and replacing with a 95% efficient, but it should do the same with 25. It should do the same job with 25% less fuel. It should. I'd like some math. It should, Bill. I'd like some math to show that. So that's why I would go through the math personally. Because if I were a consumer, I'd want to see your work. That's me. There may be other customers that look at it differently. Me personally, and I'm only talking about me, I'd like to see the math. But that's, again, because I went through this with nothing to stand on and I was embarrassed. I'd like to have a solid ground to stand on. But again, that's just me, Bill. That's just me. Here's one from William Sherman. Going back to the higher maintenance requirements of modulating boilers, service anything at home these days is very expensive. How does this impact the cost comparison of boiler efficiency workout? It doesn't impact the efficiency unless you don't do it. Okay, if you don't do the maintenance, I think that's part of the equation. Okay, that's part of the if you're going to give a customer a quote for a new boiler, I think a maintenance package is a must. Because up front, you got an old cast iron boiler. This is a different dog. All right, this is a different dog, and a different dog eats different food. Different dog needs to be walked different. All right, this dog needs different maintenance than what you had before. So we need to take care of it, and we need to take care of it so it gives you years of trouble-free service. All right, because I'll tell you what, that's an let's try that out again. New day with the first day with the new mouth. Let's take a look at it this way, William. A friend of mine once had a really interesting statement, and this was back in the 90s about high efficient boilers. And he said that he looks at high efficiency boilers the way you would look at an Italian sports car, like a Lamborghini or a Maserati or something like that. They drive awesome. They're so cool. They're fun to drive, but you better know a good mechanic. Okay. And I liked the way he packaged that, because without good maintenance, if say a blower motor dies or something goes wrong with that boiler inside of 5 years, and you have to outside of the warranty time, and inside of 5 years, and you have to replace something like a blower motor or an ignition igniter or something like the ignition module, all the money you saved in fuel just went poof. All right, you lit a match to it. You put it in a pile, and you set a match to it, and it's gone. So that's why that service is so important, to make sure it works and works well. Okay. Just understanding there's always going to be something. There's always going to be something. So again, there's factors that you want to take into account there. And again, it's maintenance is maintenance. Efficiency is efficiency, and their cost of ownership both include cost of ownership. Why do we not factor in emitters, and potential water temperature drop with a 95% boiler? Well, you kind of do. It's kind of in there. I mean, there's math-wise, it's kind of hard to figure out because each boiler is going to be set up a little bit differently for the different applications. I think you can make a blanket statement, Zach, that if I got a low temperature application, meaning that boiler is in the 120s, all 120 max in the dead of winter, and it goes lower as it gets warmer out, that's going to be a more efficient system than setting up a ModCon boiler to make 170 or 180 degree water under design conditions and then resetting. So I think, yeah, you can certainly make a statement. And I forget the math there. Was it for every 3 degrees you lower water temperature, you gain 1% in efficiency? That sticks in my head, and I'm not sure exactly how accurate that is. Okay. But in terms of just, straight up and up comparisons, this form is kind of the best we have. I think everything you mentioned, Zach, is absolutely valid, and those are kind of like cherries on top of the sundae. Okay, they'll only factor more in favor of the new and more efficient equipment. If you can't change the emitters, all right, if the emitters are the emitters, and this is a replacement application, the emitters are the emitters, and you're not doing anything different, you kind of keep it straight to straight. But again, outdoor reset and potentially lowering the water temperature, which you can do if you do the math right, and you know what the emitters do, you can lower the water temperature. That's only going to help the situation. So yeah, you should factor that in. It's a little harder to quantify numbers wise. All right. Omer asked, would you say a Delta T pump would be better to help boilers get the correct Delta T across that heat exchanger, more fuel savings? Absolutely, absolutely. Delta T pumps, to me, a Delta T circulators, our VT2218, going to be about the best pump you can put in, for the money. It's not the least expensive circulator, but in terms of performance, in terms of enhancing efficiency, absolutely. Now, there are plenty of people who have installed that circulator as the boiler circulator for a ModCon boiler, and it's set up to give you the Delta T across the heat exchanger for which you've designed, and that's a terrific application. Some manufacturers are cool with it, some aren't. So always check with your manufacturer. In the big picture, I would say learn how to properly size your boiler circulator. Bigger's not always better. Bigger's not always necessary. All right. Look, they give you this really cool free book with every ModCon boiler you buy. And in it, there's a bunch of charts that'll help you figure out the flow and head that boiler circulator needs to have. And it's remarkable. It's remarkable how small those pumps need to be. All right. So again, it's a great way to enhance the efficiency of that system. Don't oversize that boiler pump. And then properly size your system pump. A Delta T pump's a great way to go about that. Absolutely. Have you ever performed a cost comparison of a high efficiency boiler versus other systems available in the market like VRFs, et cetera? I know heat pump does not perform very well in low ambient. I personally have not, Allie. I'm sure a lot of people have. I personally have not, so I can't answer that one with any kind of credibility. I guess that would be maybe the best way to put it. Heat pumps, interesting. Air to water heat pumps. We're learning more and more about air to water heat pumps, and they can work at fairly low ambient temperatures, as low as -4 Fahrenheit. Ones that we have seen, and then one that you might see, oh, I don't know, in June sometime. There's electric resistance backup to help keep the output up under really low low temperature conditions. So the lower the temperature is, the more electric backup you have. You get below -4, you're going to need something else, all right, to serve as a backup there. But heat pumps, the new age heat pumps have some ability to work at fairly low ambience, which is good news for much of North America anyway. So that's pretty cool. That's pretty cool. Did you discuss outdoor reset and how it affects efficiency? Very obliquely, Jerry. I hope we got that. Again, outdoor reset, the warmer it gets outside, the lower temperature the boiler makes. And you select different parameters, and a lot of these boilers now have intelligence inside that can help make it as efficient as possible. And you compare outdoor efficiency with turn down ratios, or outdoor reset with turn down ratios, you really start to maximize overall boiler efficiency. And again, I think the ratio I'm keeping in my head was, for every 3 degrees you lower water temperature, you cut fuel consumption by 1%. Laundry rooms, there's usually lint. What was your experience with lint in atmospheric boilers? Oh boy, yuck. If you're not careful, yeah, you can get lint in atmospheric fired boilers, and that can create all kinds of issues. I can experience specifically, you can clog up the orifice, you can clog up if it carries the air into that system, you can clog up everything, and that becomes another maintenance issue. Oh, absolutely. Yeah, we've heard horror stories about that. This is where I make my per session plea for a VR-sized VT pump. All right, Zachary, duly noted, man, duly noted. Do you see this kind of pump being a must in boiler company design? Asked Homer. What I think you're going to see, because you're already seeing it in larger boilers, is 0 to 10 control output for a 0 to 10 pump, 0 to 10 volt pump for the boiler pump. And once you marry those two together, then the boiler itself can tell that pump what speed to go to optimize the performance. We already see that in larger mod cons. We're going to start seeing it in smaller ones, I think, in the coming years. So I think that's really the best way to go. And that heat pump thing I alluded to earlier, there are a couple of 0 to 10 pumps in there that we can discuss at another point in time. I guess that's as much foreshadowing as I can give you on that. All right, good. Excellent questions, folks. Excellent questions. Keep them coming in, man. I appreciate the interaction. This is what makes these sessions so interesting and so much fun, I think, from our end, and hopefully from your end as well. So give me a little bit of feedback. How useful was this session for you? It gives you a starting point. Does it, as many point out, does this include every factor conceivable in terms of efficiency? No, but it does include what we can quantify. It does include that. When it comes to high efficiency boilers and outdoor reset, I think, boy, it was Dave Holdorf had a stat that just blew me away. I think it was like over 50% of the ModCon boilers installed out there did not have the outdoor sensor installed. Don't need that problem. Okay, don't need that problem. So interesting stuff. It boggles the mind that you'd install such a high efficiency boiler and then not install the one thing that makes it work. But that's the world we live in. So again, there's for the sharp service guy, there's still a lot of money to be made out there fixing things that like that. So yeah, just an interesting concept, interesting challenge out there. So anyway. 44,000 BTUs, 2400K, 18.33 BTUs per square foot. Yeah, that sounds about right. Yeah, we should have had a handout with the equations and the definitions. Yeah, I'll grant you that. That's probably next time we do this presentation, James, I will put that in there. But just remember, you will get a copy of, you will get the recording tomorrow, so you'll be able to glean all that from the recording. So yeah, but good point. Probably should have done that. In my rush to get all the handouts in, that's probably one thing I could have put in there. So good call there. We always learn, man. We always learn and we always strive to do better. So appreciate that input. Excellent. Well, hey, like I said, folks, I will stay on as long as y'all want to. The official presentation's over, but any questions you folks have, just fire them away now. Now it's open topic. Anything you want to know about TACO. Omer asked, what's my favorite TACO pump? I think you know the answer to that. That'd be the VT2218. I love that baby. Delta T pumping is absolutely the way to go. If you want to vary a speed of a circulator, shouldn't you vary the speed in a way that accurately reflects the load? All right, and the load is going to be determined, the delta T is going to determine the load. Remember, the universal hydronics formula states that GPM, your gallons per minute flow, equals the BTUH load divided by the product of delta T times a constant. In this case, we'll use 500. If the speed is constant and the BTU load varies, logic and math tells us the delta T has to vary, okay? As the BTU load goes down, meaning it gets warmer outside, the delta T gets smaller. As the delta T gets smaller, because the flow rate's the same, right, with a fixed speed pump, as the delta T gets smaller, well, the return water temperature going back to the boiler gets higher the more we short cycle. If, however, we are able to keep the delta T fixed for as much of the heating season as we can with a circulator that will vary its speed to maintain that fixed delta T, well, as the BTU load changes, if that delta T is fixed, the flow has to change along with it. And that's when you start to get efficiency. Now we're always bringing the lowest potential water temperature back to the boiler to enhance, to lengthen its cycles, number one. That's just common sense, number one. Number two, you want to bring the lowest possible water temperatures back to the boiler, don't you? It's just the way to do it, right? All right. Well, TACO get into providing products for tankless water heaters like air vents, service valves, recirc pumps. Already there with air vents. Service valves specifically, I'm not sure where you're going with that one, Omer, but please clarify. Recirc pumps, oh God, we have recirc pumps for everything. With tankless water heaters, the interesting thing about tankless water heaters and recirc pumps, most have their own setup internally. What we're finding, OEMs, most have their own setup internally, and we're working with different manufacturers to provide solutions there and come up with solutions. If there's a tankless without its own internal recirc setup, well, then what you're looking for is something that's going to be on demand. All right, and we have the TACO Genie that will do that. Now, a lot of people say, well, hey, that TACO Genie is not ECM. You know what? In an on-demand with a tankless water heater, you want to be able to manually enable that pump, right? And that's Title 24 as you get out in California. Otherwise, you want to be able to manually enable that pump, push button, or remote push button, motion sensor, that sort of thing. And at that point, you want, bam, you want a high head pump. You want to evacuate that hot water line of cold or tepid water as fast as possible. That means a little bit more powerful pump, but a very short runtime. Our Genie might run 20, 30 seconds at a time, and then it shuts off because it's done its job. It's delivered the hot water to the fixture. ECM circulation is not going to help much there. I get where the market's going. It's going to have to be ECM, but it's one of those things where if you discount it because it's not ECM, you're stepping over $1 to pick up a dime. It doesn't make a whole lot of sense. So that's just kind of the way I look at on-demand recirc circulators. Okay, partnering up with brands, absolutely, Omer. That's something we do all the time. We have an OEM department that's looking at all of those opportunities. Paul says the VT2218 is key to our patented hydronic appliance performance. Ooh, boilersondemand.com. I'm going to write that down. I'd like to check that out. That's pretty cool. Boilersondemand.com. I got that written down, Paul. Thank you. I want to take a look at that. Appreciate that. Excellent, excellent. Oh, very good, guys. It's so good to be back. It's so good to be doing this again. We took a few, we ended up last year. All right. January, we had a lot of stuff going on internally with meetings and planning sessions, and then getting ready for the AHR show, which was terrific, by the way, in Las Vegas. good to get back in front of people. That was, even though the show was a little bit smaller than normal, good to get back in front of people to talk to customers face to face in a large arena such as that for the first time since 2020. So it's been 2 years. So it was really, really, really good to be able to do that and see a lot of old friends and make a lot of new friends. So that was awesome. That was really awesome. So we're really glad to do that. So that's why we're starting Takeo After Dark tomorrow night instead of back in January, and starting these today instead of back in January. Just January was a big jumble for everybody. Now we're ready to go and back at it. Tomorrow night's Takeo After Dark should be a hoot. If you want to go, if you haven't signed up, go check it out on our website, takeocomfort.com training, and you can sign up for that for tomorrow night at 7 p.m. Eastern time. All righty. Anything new behind the scenes? Well, yeah. I think I alluded to one of them there on a couple of occasions, Omer. Yeah, just keep your eyes open. Keep your eyes open. I'd say June. It's something very unique and very different for us that I think is going to be very interesting, depending upon where you are in the country. It's going to be it could potentially be it's going to be a unique niche product to start, but the more people understand the features and the benefits of it, I think it has wonderful potential, and it solves a lot of problems, particularly if you struggle with finding help. This is something where it's modular and it's going to be interesting. I can't wait to be able to talk about it. And well, we had it at the show, so I guess I can talk about it. It's an air-to-water heat pump called the Takeo System M, and it's modular. We've got an outdoor unit and a factory-made, wired, and ready-to-go indoor unit that includes your circulators, your buffer tank, the entire control strategy, everything, all set up and wired. All you need to do is run power to the outdoor unit, power to the indoor unit, 6 piping connections, 2 piping connections to connect the indoor to the outdoor unit with water. The outdoor unit, it's a monoblock system, so the outdoor unit refrigeration is all factory sealed. All right, so you connect the indoor unit to the outdoor unit, then you have 2 pipes for your heating, cooling, and 2 pipes for your domestic hot water. And that goes to we also are offering an optional 85-gallon indirect, and that gets pretty cool. And that's it. And you can connect to an air handler. You can connect to an air handler and other types of hydronic types of low temperature hydronic. So we're good up to about 130-degree water, and boy, it's exciting. I'm learning so much about air to water heat pump stuff I never knew before, and it's a new world, and it's a fascinating world. And I think that's for the right applications, it's going to be a real interesting solution for the contractors who really want to do great stuff. And the programming is super simple, controls all the operations. Rather than piece it together on your own, it's all there for you and all wired and ready to go. So it's very cool, very cool. I hope that answers your question, maybe whet your appetite a little bit there. That's good. All righty, folks, last call for questions. I still have 113 of you out there, so let's see what we got. Okay, here's one from William. Do you think boiler manufacturers will embed remote equipment sensing for troubles? Be a good idea, wouldn't it? I know of one heat pump that might. Just saying. That you teed that one up very, very nicely for me, William. I think so. Again, it's going to become more important, so you can check on what's going on there. I think that. I think it's the technology's there. It's just a matter of installing it and what the cost is and who uses it and who has access to it. I would think so. I can't speak for them because I don't know, but I could see that happening. I could see that happening. Adam says, excited to see the air-to-water heat pump. We've been working with Minnesota Power on a residential heat pump project. Oh, very cool, Adam. Hey, drop me a line. All right, it'd be interesting to hear what you have there. It's a JOH. Let me type this in for you so you'll know what the email is. But yeah, please drop me a line. I'd like to know a little bit more about that. And takeocomfort.com. All right, I'm gonna send that to everybody. There's my email address. Shoot me a line on that. I'd be interested to hear what you have to say. All righty, the Middle East market for the heat pump. Yeah, it'd be interesting to see what the Middle East market is. That would be kind of cool too, because cooling up to 100 and it's good up to 100 and is it up to 115? I think cooling wise, it's good up to 115 degrees. It gets warmer than that out there. I don't think you're going to need some other help, but yeah, that'd be kind of interesting. Yeah, air to water heat pumps. Yep, as a plumber, the existing ones are very frustrating to work on. Well, I think you might find these interesting, Micah. Hopefully anyway. All right. As always, your fountain of knowledge. Oh, thank you, Omer. That's very, I appreciate that. Thank you very much. Thank you kindly. Alrighty, folks. Hey, thank you for being with us. Really do appreciate. Oh, more coming in. No, more coming in. So you got to get back there. More coming in. Let's see what we got. I did not find the 3 degrees to 1% efficiency, but dropping the delta T. Makes your system more efficient. Okay, that works. Yeah, again, I remember that from many years ago, Bill. And I think it came from Viessmann, if I'm not mistaken. Every 3 degrees, you drop your water temperature 1% efficiency. You gain 1%, or you cut fuel consumption 1%. That's different than saying efficiency. It's because the efficiency is a percentage. I think for every 3 degrees you can drop your water temperature, your boiler water temperature, you reduce fuel consumption up to 1%. That's the way they counted that. So that might be kind of interesting. All righty, very good. Let's see what Jeffrey says. Pay close attention to how Water Furnace provides Symphony Wi-Fi monitoring on their Geo units. Dealers can see 57 plus data point conditions for operation at 10-second intervals. It's way advanced over in Everling. Oh, very good, excellent. Yeah, we'll take a look at that. But I just gotten a cursory look at our stuff. There's an app that you can use from anywhere on the planet to see what's going on, and additionally, our tech team can see everything. It's pretty cool. It's in terms of service. So if you were to call us up and say, "Hey, I have a problem with this heat pump," we get the IP address. It's connected to the internet. We can look in and see everything. It's really cool. It's really pretty cool. It's really pretty cool. All right, excellent. Well, thank you, Vincent. Appreciate the kind words. And Sarfraz, thank you very much as well. All righty. Now I'll do the last call for questions. You guys, every time I say that, you guys have a way of sneaking a couple quickies in there on me. So good. Alrighty, hey folks, thank you so much for the gift of your time. We really enjoyed spending this time with you, and really looking forward to seeing you next week. Will be a commercially focused session on pump fundamentals for commercial applications with Rich and Brett, and those folks. I sit in awe of their knowledge, man. They are really the best in the business. So that's really those are always so much fun to listen to. And we'll be back in 2 weeks with another residentially focused session. So thanks again. Have a wonderful Tuesday, and hopefully we'll see some of you tomorrow night on Takeo After Dark. And have a great day. Take care, everybody. Bye-bye. Well, hey, good afternoon, everybody, or good morning, depending upon where you are. Welcome back to another Takeo Tuesday extravaganza. I'm John Barba with Takeo Comfort Solutions, joined by the two best trainers I know in this industry, Dave Holdorf and Rick Mayo. How you doing, guys?
Yeah, very good.
Thank you all for being with us today for another edition of Takeo Tuesday. And as the sign says, we have a terrific program for you. Again, one of my favorites. It's going to be on ModCon boiler piping, and most importantly, ModCon boiler pumping. And taking care of the duties today is maybe the best presenter on this particular line of information that I've ever seen, and that'd be Rick Mayo. So Rick, I'm really looking forward to your presentation today, and I hope everybody else out there is as well. A couple of things, again, just to get us, if there's a lot of first timers out there, I want you to understand the control panel basics, particularly how to ask questions. So if you take a look at the control panel, you should see a little orange arrow on the right hand of your screen. If that arrow is pointing to the left, that means the screen's minimized. So click on that and it'll expand your control panel. And the upper portion you'll see is the audio section, just to make sure you get the right speakers selected, etc. There's also a section for downloads. We do not have any downloads for you today, but in future ones, we most certainly will. And finally, down at the bottom is the most important part, and that's how you're going to ask questions. And we do encourage you folks to ask as many questions as you want to during the course of this hour. One of the things we do at TACO is we don't ask you to hold your questions till the end, because that's kind of lame. What we'd like you to do is ask them as we go along, okay? Ask your questions as we go along, and we'll take a break every few slides to start to address some of the questions that you have, and we'll stay on at the end. As long as you guys have questions, we'll stay on as long as we have answers. So so we will be available after the class for as many questions as you have. If you could all do me a favor right now, just to know that everybody out there kind of knows how to do this, could you just type in a hello, how are you, whatever it is you have in that question chat section, so I know that you know how to do this, and I know that you can hear me. That's the other important thing. Okay, very good. We got a lot of hellos. Excellent, terrific. You guys got it. And please make sure, just type in your questions as we go along, and we'll be able to really make this a really fun and interactive as possible in this webinar setting presentation as we can deliver. Now, if you happen to be on like a tablet or a phone or something, it's a little bit different. Just down at the bottom is your control panel. You have a little screen toggle where you can go back and forth between webcams and presentations. Your audio settings are there, and that little question mark, obviously, if you press on that, that'll be how you can type in a question for us. So just so you have that all set and ready to go. And with that, without any further ado, I would like to turn it over to Rick Mayo. Rick, I'm going to hand you the con, and you can take it away from here.
You tell me when you can see my screen.
All right, I'm going to make you the presenter. There you go.
Show my screen.
Hot diggity. There it is.
There it is. Thank you.
All righty. And
all right,
both Dave and I will visually be saying goodbye, but we'll be right here to help out with the questions.
Visually. Okay, cool enough. Let's go ahead and jump on in. Thanks for the introduction. Thanks for everybody showing up. And this is a topic that is near and dear to my heart, but most everybody in the hydronic heating business as well. So I will say this as kind of a preface as we get into, what we're talking about. We're doing this for a reason, right? And one of the things I hit a bunch of slides that were the first part of this presentation, but for the sake of time, right? But one thing I didn't want to not convey is the importance of low temperatures back to a condensing piece of equipment. In this case, we're talking about condensing boilers, right? So, there's the magic number, right? And I guess my point is this: I want to make sure you realize that there's a goal we're looking for here. It's low temperatures back. If you look at this chart that comes to us, I've seen this from ASHRAE, and almost every boiler manufacturer out there that sells condensing equipment uses something that looks just like this or similar to this to some extent. But you notice there's this magic spot in which the pitch of this curve changes quite a bit, right? And this spot here, it's pointing out that it's 135 degree dew point for natural gas flue products. But that's not the number we're looking for. That just tells you the science is happening back inside the combustion chamber and stuff. What we're looking for is a fluid temperature that's low enough so that the surface temperature can actually see condensation. So we need low fluid temperatures, and a lot that has to do with a couple of things we're talking about here, like John already mentioned, piping configuration and pump sizing has to do with getting this efficiency up where it belongs and keeping it that way, maintaining it, sustaining it, etc. So why don't, since I can't see the answers, I'll depend on John and Dave to give me some feedback. Who wants to throw out a nice round magic number for the return temperature back to a condensing boiler? Go for it.
We got a couple of folks who did not hesitate whatsoever with those numbers. I have everything ranging from 130 to 100.
Oh, okay.
We got a 160 in there as well.
Okay. Well, 130 is the magic number. It's round. It's rounded, I should say. And of course, down here, keep in mind, the lower the better. So whoever's talking about 100, yes, amen. That's what we're looking for. So again, I just wanted to preface that. This is what we're doing here. Now, one of the things that comes up is how do you pipe a condensing boiler? Now, you pipe it the way the boiler manufacturer tells you and shows you in the back of their book. All the back of their books are really good. They're getting even better from 20 years ago when I was kind of messing with this quite a bit, as far as giving you more information. And so some of the things I'm going to talk about are generalizations, but always refer to the boiler manufacturer's manual. They'll give you what they want and why they want it, hopefully. But since a lot of those manuals tend to talk about piping in a particular configuration, we're going to focus on that, and that, of course, is primary secondary. Well, primary secondary when we're talking about boiler piping has to do with the separation of the circulators within the system. Now, the one that's on the boiler should only be affected by anything that's in the circuitry of the boiler. That means the heat exchanger, the near boiler piping, the closely spaced T's, the hydraulic separator, etc. Okay, that should be its only worry. And then the system circulator or zone circulators that are on the secondary side, those should only be affected by what they're responsible for. So it's actually just separating the lines of responsibility and making sure that circulator is only doing what it needs to do. Again, this came up in one of our other sessions last week. We were talking about low loss headers, use that in quotations. And where did that term come from? Well, that term came from a device that kept the pressure drop of the heat exchanger of the boiler out of the responsibility of the system circulator. Okay, and so it gave us some of the things that we're looking for. We're not going to focus on that so much today, but we call them hydraulic separators or low loss headers, but that's the reason it was called a low loss header, because we didn't want the pressure drop back in the early days of condensing equipment, which was relatively high, to be the responsibility of the system circulator. Okay. So anyway, the boiler manufacturer nowadays can and may control the primary circulators, that's the boiler circulator, that can control its speed. We'll talk about that a little bit as well. And it's actually, if we can do that, we want to do that and take advantage of that as well. One of the downsides of primary secondary piping is you have the possibility of short cycling water from the supply pipe that goes into the closely spaced T's backwards, I should say, and back up and into the boiler. And this will happen on some occasions. What we're trying to do with this little session is make sure you keep that to a minimum. Okay, and we'll show you what that looks like. This is just words on a bullet right now, but we'll get into that. We'll talk about what that really means. Okay, and again, refer to the boiler's manual. It shows you what they want, what's acceptable, what's not acceptable. One thing I will throw out with this in mind: if the boiler manufacturer allows you to pipe the boiler in series, that means not primary secondary. Some people call it direct flow or variable primary, or there's some other terms out there. If they allow you to do that and your system affords you that opportunity, then by all means do it. Then some of these things that we're talking about in primary secondary don't need to even be considered at that point in time. But there are some caveats to that, so that's why I say just follow the boiler manufacturer's manual, and you'll be safe. Okay. Let me ask a question. Give me some quick feedback. Anybody pipe like this anymore when we're talking about condensing equipment? Okay. And I'll call this a boiler loop. Okay, that's where you come out of the boiler, you make a nice big halo or a big loop, and then off of that you do your closely spaced T's, and you take care of your highest temperature first, next highest temperature next, etc. Anybody out there still piping this way? It's kind of a throwback to the early days of getting multiple temperatures on a traditional cast iron atmospheric boiler. But some people have taken that concept and kept it with condensing equipment. Any answers out there, guys? Anybody, anything coming in?
I have one one emphatic no, and then one occasionally where requirements are correct. We got a not anymore, we got a no, and a no uses separator near the tank. And then we have a yes working with an engineer now that refuses to change it. So
Okay.
we're kind of all over the map there. So yeah, okay,
We're
great.
all, we got a mixed bag, as they say. Very cool. So I'm not going to elaborate on this. I will say that we're still talking about boiler circulator sizing, right? We're still talking about closely spaced T's, and all that applies. Okay. Here's what we typically see nowadays. Most of the boiler manuals out there, they're showing, for instance, this is depicting a wall hung condensing boiler. This is kind of how they show it. We have the near boiler piping, which is just relatively short. It comes down and goes into the secondary portion of the system, right? So again, we're going to focus on these two things here. We're going to highlight this. It will be a little bit of review because we talked about this in the last couple of episodes of TACO After Dark, and that's a plug for TACO After Dark for those who are sitting here for the first time and haven't heard about TACO After Dark. It's an evening session. I'll let somebody elaborate on that later, but we talk about things like this, and we might get into a little more detail. But one thing that I mentioned on one of my bullets is the ability for the boiler manufacturer now to have control of the circulator. So what I'm saying is a pump manufacturer like TACO now gives the keys to the boiler manufacturer. Here's the keys, you run me however you see fit. And we're doing that with typically in North America 0 to 10 volt DC signal down to the circulator. This is not just powering the circulator, it's saying, look, I'm going to power the circulator and I'm going to control its variable speed based on input that I'm receiving from something that's within the boiler manufacturer, right? The boiler manufacturer always is looking at supply and return temperatures across its heat exchanger. It also, in some cases, has the ability to look downstream, maybe put a sensor out over here and look at the secondary portion of the system. Okay, the system side of things. So again, understand that that's all information that the boiler's making decisions on, and it now has the ability to ramp this circulator up and down to maintain something. The majority of the people that have had success doing this, that input is based on a temperature differential across its heat exchanger. Okay, we know that as a boiler modulates its flame up, we're adding more energy to the fluid within the heat exchanger. Well, the telltale sign of that is a big increase on the supply water temperature. So if it sees a delta T that starts to widen, that's its signal to say, hey, if it goes beyond what you want it to, and says, hey, giddy up, pony, let's get some more pumping going on, and let's pull that energy out of the heat exchanger and send it into the secondary and tighten up that delta T. Okay. And on the other side of the coin is, hey, if we see delta T's that are too tight, tighter than they should be, then let's slow that circulator down and let's get back into a lower return temperature and kind to stop that that water coming across these two T's that I spoke about earlier, right? And I'll get into that. Anyway, understand that if you have the ability to do this, this is a good thing. The only issue, and TACO makes circulators in the kind of the mid-range size and the light commercial size that have 0 to 10 technology. Most everybody, and including us, they're little tiny pumps. In our world, it's a little 44-watt circulator. Currently doesn't have in an ECM offering the ability to have that 0 to 10. So what my next slide is going to talk about or just touch on will tell you why we're still talking about things. Otherwise, we just say, always do this. The problem I see out there, especially with some other products that come packaged with some competitor product on it, is there's an old saying out there, you can't go any lower than low. And if you put a circulator on there that has 0 to 10, but is physically too big of a circulator for the job it's being asked to do, then it just kind of sits there on low speed. It can't go any lower, and therefore it cannot widen that delta T any more than low speed. So a lot of you know where I'm going with that, but maybe I should open it up if there's any questions as it relates to that. And if not, I'll continue on. Anything out there, boys?
Here's a quick question from Carmine. What is the valve shown below the circulator, below the boiler circulator in the system piping?
Right
there,
would it be this?
Yeah, I think that's what he means.
Oh, okay, that's a magnetic dirt separator. That's our 4900 series magnetic dirt separator. And that's just to protect everything that's going back to the boiler in this right there. Okay, so hopefully that answered that question. Yeah, I wouldn't think this is just an isolation valve. This is a check valve that just happens to be part of that circulator package, and another isolation, a boiler drain. No, I think that's what you're talking about right there.
Yep, he does, and he said thanks.
Okay, cool. Let me go back. So the reason, notice no more control wire. It's very important now to get this circulator size correctly. And we will talk about that. We'll give you some hints and some things that in some cases kind of changes the way you've been thinking about things. I know others have noted that and just saying, yeah, I've been oversizing that pump. Well, that's what these seminars are supposed to do, is get you to quit just doing the boilerplate stuff, right? Start thinking about what you're doing and why you're doing it, and be able to back up, why you're doing what you're doing. And that's what TACO's trying to do here, trying to make sure you have a better understanding of why you do what you do and why you size the way you do, et cetera. So we'll focus on this circulator. I will say this while we're on this slide, that the mode of operation, remember these ECMs have all kinds of modes of operation. Well, the only thing that makes sense in this near boiler pump application is that 0 to 10 or 4 to 20 milliamp, or there's some other things out there that's being done, pulse width modulation, some other things. One way or another, if you have that control, fine. But if you don't, there's only one other mode that makes sense, and every ECM has it, and it's called fixed speed. Some people call it constant speed. But what we're saying is there's nothing within this circuitry. If you look at it, there's a boiler's heat exchanger, there's some piping, there's a T here, that's the circuitry that's responsible, that this circulator is responsible for. There's nothing that's going to give it a hydraulic change so that it would have the input to make a decision to speed up or slow down. So do not use an automatic mode for that pump. Okay, it just won't ever get the information to change its speed. It may or may not be enough. Now I'll show you one application where we're going to say, go ahead and do this, but it's only once you've dotted your I's and crossed your T's, and we'll show you that, okay? By all means, it's being done, it's done successful, but it doesn't make a lot of sense if your expectation is that the pump's going to speed up and slow down, because it will not. Okay, primary, secondary configuration, a little bit of review. Like I said, we've done this a little bit this year already. So again, I can't just assume that everybody that saw that is going to see today. So I'm going to talk like it's fresh and new and all that stuff. But it is the rules of primary, secondary piping in a condensing boiler application specifically. It's as easy as ABC, right? So what are the rules? These are, again, we always trying to get you to understand concepts more than numbers. We always talk about doing the math, and we show you numbers, ad infinitum, right? But ideally, I think it's better if we can leave you with a concept that just sticks in your head. The concept is good. If you have the concept down, you won't ever have to worry about the numbers. That's not to say that the numbers aren't important. It just means if you're like a lot of people, especially service guys, plumbers, and things like that, once they get a concept down, that it's locked in. They might not remember all the little specific rules and stuff, but the concept works. So again, we're going to try to get two things accomplished here. Make sure that you understand the concept more than anything, and go ahead and give you the rules, just if you want to take notes, as we like you to do that, and we like you to clarify and question and things. So let's go with that. So this A right here, this is depicting the distance between these two T's, right? And some people have said, well, is it on center or is it edge to edge? And You know, it doesn't matter that much, okay? And for the most part, it's edge to edge. How much length does this short little piece of pipe need to be, okay? Now notice this too, this says maximum. When it says maximum, don't pull out a ruler and cut it that length. Because again, the concept is get this piece of pipe as short as possible, right? You want that piece of pipe to be as short as it can be, literally, to make up those two T's that are closely spaced. Okay, so and we're talking about here not inches but pipe diameters, and it's of the pipe that's on the secondary side. In this case, the boiler's coming in and back up into this portion of the system piping, right? So what size is this system piping, the secondary piping in this case? You know, whatever you want, if it's 1 inch, etc. So it's easy to do math, okay? Don't exceed 4, but actually make it shorter than that, okay? The closely spaced T thing here is, this is something we do, and I think my camera is the only one that's on right now, but if I put my hand up and I say this is 1 T and this is 1 T, and I put those 2 T's together, and it's right in the middle of a nice long piece of pipe on each side of that T, right? I'm doing really good. That's the concept. That's what I'm shooting for. So anybody that wants to join me and won't be embarrassed sitting in your office doing this with me, they'll want to say, hey, is that just 2 thumbs up? Well, you could call it that, but it's closely spaced T's, and a good way of understanding that concept and keeping it with you. Okay. Of course, that leads us to the B note. Okay. Now, again, I've got an arrow here to show you what I'm talking about. From here, going this direction, from left to right. Now, the minimum amount of pipe diameters is 8 coming into this first T. Okay. And we'll show you on this next slide a little more detail on that. But here's, you know, I'm giving you the concept and I'm giving you the rule. The minimum is 8 pipe diameters of this secondary pipe. Okay, remember, and as close as possible here, but downstream, since we've already done the job that we were meant to do by getting this water mellowed out, and I'll show you what I mean by that in a minute, then once we've done that, then we only need about 4 pipe diameters on this second side as a minimum. Again, conceptually, 2 T's in the middle of a nice long piece of pipe. Okay, understand that concept, you'll stay out of trouble. The C note here is just actually having hotter water higher than the water, so you get some thermal trapping going on. And again, that's kind of a throwback to the variable speed injection mixing. We're not going to spend any time on the C note, but just try to remember that the hotter water needs to stay higher than the cooler water in mixing primary secondary. Okay. Here's just some words out there, right? I got, you can see I've got what's depicting smooth flow and a chaotic flow. And some people would say what? You know, they'd say chaotic flow is turbulent, smooth flow is laminar. Well, you could use that terminology if it works for you, but if you really look up turbulent flow and laminar flow, it doesn't necessarily fall into this category. So there's just terminology, so I changed it up a bit. But notice this, if I come out of this circulator downstream right after here, I'm going to be in a chaotic flow pattern because of what the circulator did by adding that mechanical energy to the fluid, right? It's going every which way. But once it goes out on this straight piece of pipe for a certain amount of distance, then it goes from this chaotic flow back to a nice smooth flow pattern before it gets to this first T. This is what we're talking about right here. And again, this is nothing that TACO has done. This was done years and years ago in the mid 50s. Guys in white jackets in laboratories testing this stuff with pressure gauges and temperatures, and all this stuff's been established a really long time, but well before I was born, and I'm an old man now for the most part. So again, this stuff works. Once we get enough straight pipe, uninterrupted pipe, then it goes from one flow pattern to another, and that's what we're shooting for. We want a nice long straight piece of pipe before this first T. Okay. Now there's been talk, well, how much distance do I need here? Well, if I've already done the job, I can actually butt these up. There's been some pre-assembled panels and some things like that that have been sold for years and years that never followed, you know, B plus B again, right? They were right up, and it works pretty good. So again, if you remember the concept, if I can make this longer, then by all means make it as long as you possibly can. If you wanted to do 4 pipe diameters and 8 pipe diameters for a total of 12, by all means do it. Okay, it would be a good thing. Okay? Hopefully that makes sense. And if there's any questions on that. So just a little review here on pipe sizing, right? We're just talking about the maximums that are out there. And again, whenever you're talking about pipe sizing, you should probably just figure out which pipe you're talking about, what type of pipe and what size is it. In this case, this little chart just referencing type L copper, okay? But notice there's a couple different columns that say maximum. Notice maximum, maximum. This one is 4 feet of head per 100 foot of pipe, and this is 4 feet per second. Those are 2 different ways that we look at maximums in our industry. And just again, since this is review, a lot of you folks have seen this before, but just the idea is doing the right pipe size helps quite a bit, especially in overall pressure drop and things like that. Remember that typically down to 1.5 inches covers us up to most residential applications, and starting at 2-inch and bigger would cover most of our commercial range, right? So notice one thing that's significant about these maximums. Right where the colors change here from green to red, and residential goes to commercial, it also flip-flops in the amount. Notice this column gives you more flow than this column until you get to 2-inch, and then this column gives you more flow capacity than this column does. So no, you guys that are out there doing work that kind of goes into commercial, just remember where you can flip-flop to your advantage, okay? Use what's you know, within our industry's acceptance that is to your advantage. And when you remember things like this, it helps out quite a bit. So,
Rick, we have a question.
Go ahead.
Sorry, we do have a question about boiler piping and system piping. Can they be the same size?
They can be the same size, especially if you go back to where we were talking about piping in series, right? So that way the total flow of the system is going through the boiler. With that in mind, you would want the same pipe size. What we see in primary secondary quite a bit is that we're using a bigger delta T across the boiler side so we can get by with smaller pipe sizes. For instance, we might have 1-inch headers coming off a condensing boiler that go into an 1.5-inch secondary system pipe. Hopefully that answers the question.
Right. And oversizing the system pipe, you know, that oversizing the header is actually a good thing. It simply aids in hydraulic isolation.
It does on that close near boiler header,
right,
for multiple zoning. Absolutely, that's your near boiler piping secondary header, and it wants to be generously sized or copiously sized, however you want to say it.
Well, they can be like me, short and fat.
Yeah. Well,
There
if you want to go back and look at it, when we talk about, this right here, if you keep those secondary headers in and around 2 feet per second, that's kind of a heads up that keeps them nice and copiously sized. Okay, so use your 2 feet per second on that close near boiler piping header for multiple zones, and then use 4 feet per second for your maximum velocity out on those secondary pipes or anything. Generally speaking, this would be your maximums. So
yeah,
that's all this slide does. It just reminds you, if we stay between 2 feet and 4 feet per second, we're in the sweet spot, folks. You'll stay out of trouble. Again, it's got to apply to the pipe and type that you're using, but it keeps you out of trouble. And this is just showing you at a given delta T, what could you transfer at this maximum. For instance, if I had a 1-inch pipe and I ran 10 gallons a minute through it at a 20-degree delta T, what should that be? Right around 100,000 BTUs, and it is. So just understand that. But let's look out. Let's say that we went out to a 40 on a condensing boiler. Hell, I could do 200,000 BTUs. You know, now you might not want to do that, or you might, depending on how good you feel about what's written in the boiler's manual, etc. I'll refer you back to that every time. So
Right, in reality, it's impossible to oversize a header within reason. You know, so yeah, if you want to, if the flow rate says 1 inch and you want to put 1.5 inches, it's only going to be of benefit to you.
yeah, it won't hurt you much. The only thing that would come to counter that, not counter it, but just say, hey, remember that we want to keep our at 2 feet per second or
Right.
slightly higher for the bubbles and et cetera. But again, folks, I get into this. I talk about if you do a good job of purging the big bubbles out, you know, doing a really good job of the initial purging, the micro bubbles and the little tiny bubbles aren't what really hurt us a lot. It's the big, you know, when we get a call and say this pump's not working or the boiler's going off on high limit, et cetera, it's because it's full of air and no one did the initial purge. They think just filling up the system, they think the, you know, like in our case, the 4900 does all the work for you. No, it doesn't. You have to do the initial purge correctly. So anyway, so this slide just is focusing on the sizing of this near boiler pump in a primary secondary configuration and how that helps us in the overall boiler efficiency. And you know, you folks know kind of where I'm going with this one, especially how I ended it there. You have to read the manual, and the manual is what will tell you what to expect as far as pressure drop is concerned from the boiler's heat exchanger. Okay, and I can't overemphasize this. Don't oversize the boiler circulator in a primary secondary application. Okay, it's not good for anybody. Okay, anyway. So let's focus on these two T's right here, okay? And I'm going to show you visually what happens, okay? I'm just blowing up those two T's, showing you what the ideal flow pattern that we're looking for, because we want the coolest water temperature to go back to the boiler. And if you're looking at this from the standpoint of with that understanding, you're going to surmise that if I've got water going up here and I have water going this direction, and I have this blending back in here, then this GPM is going to be equal to or slightly less than this GPM, and we're just splitting the flow here. But the idea is I don't have any of this heated water coming back across the top and coming in here. So that's why we say this is the, in a primary secondary configuration, this is the ideal flow pattern. We'll give it a thumbs up. Okay. Here's an acceptable flow pattern. People go, what do you mean by acceptable? That looks perfect to me. Yeah, but if I have primary secondary piping configuration, I have a dead space right here. Why do I even have it, right? The other thing is people say, well, you know, I've got two pumps on there. What if I just make the pumps the same size? Won't I get this as an end result? And I'll say, well, it's really hard to do. It's acceptable, but just not very practical, right? The idea or the concept of saying I'm going to put two pumps that are equal size and I'll get equal flow just goes against everything we teach you about pressure drop calculations and understanding, you know, how something within the fluid flow impacts the pressure drop. So I think most of you can give me an understanding on that. It's really hard to do without doing balancing valves and all this other nonsense. So anyway, just understand that. Here's what we don't want to happen, right? Here's the thumbs down, right? So you can see this. It kind of shows you that if I oversize the boiler circulator, I have more flow going back across here and now blending that cooler water with a heated water, and now I'm reducing the overall boiler efficiency and the overall system efficiency. So that's undesirable. Now I will admit, I'll have to say that under these shoulder conditions, these bench conditions, where you just have you know, really, you know, not really cold weather, just kind of sort of cold, you know, maybe in the spring and in the fall, etc. You're going to get this a little bit because, as I said before, even if you have a circulator that is controlled by the boiler, you can't go any lower than low. And the thing that we have going for us in those shoulder conditions is that they tend to be not really cold. They're nowhere close to a design condition. And so they're relatively short periods of time where we have this. And the cumulative temperature is still below that magic number of condensing. So I'm still condensing for the most part within those shoulder conditions. So, John, is there any questions on that? Usually, you know, that could bring up some understanding or clarifications or something like that.
One question, there was one question about would that not induce short cycling?
Oh, absolutely. If depending on what that temperature is and how far that boiler was able to turn down or not, right? So different boilers, different things. But yes, good point to make. We're not only talking about overall system efficiency, but we're talking about steady state efficiency. We really don't want that boiler banging on and off, and that's a whole nother webinar that we'll probably do down the road when we talk about buffer tanks and things like that. So.
Did have one other question about the for closely spaced tees. What does the up to 12-inch max refer to in 4 pipe diameters up to 12 inches max?
3-inch pipe. And
Yeah.
how many people are doing 3-inch pipe on this webinar right now? Now, on a regular basis, your boilers have secondary headers that are 3-inch.
That would be the 12 inches, right? 4 pipe diameters times 3 inches, 12 inches. So again, closer the better. Closer the better.
Yeah. Like I said, the problem that we see with the boiler manufacturers putting that note in there is because you take a fitter that doesn't understand the concept. Again, why you're sitting on this webinar, if you don't understand the concept, you're going to pull out a tape measure and you're going to cut a piece of pipe 12 inches because it says it right there in the manual, or it says it right there in the print. You know, so again, the concept will save you time and money and headache. And again, the 12 inches that they note in those books primarily are talking about maximum spacing. If the concept is that I get it as close as possible, yeah, I think you'll get where we're going with this. So anyway, so let's use a boiler model that's around 155. Now I've hidden a bunch of slides for the sake of time of different manufacturers. I just picked another one that I haven't used in a while, and I'm talking about Well-McLean. You can see that down here, and this is what their chart shows for their condensing product. And my point is, I'm still emphasizing the fact that you don't want to oversize the boiler circulator. And again, these manufacturers are making it even easier for you to do this if you just read the manual, okay? But I'm going to generalize some things as well, because you might not have the manual in front of you, or you might, I might be able to emphasize the concept a little more here. So what is the range that that means the boiler manufacturer, will allow? The concept here, folks, is go as far as they will allow you in writing. That way your rear end is covered and you're not getting yourself into trouble, right? So in this case, they're showing you a 20 degree, a 30 degree, and a 40 degree delta T, and they're giving you following information based on that. What to expect for flow, your initial thing you need for sizing a pump, and then what to expect on the pressure drop through the near boiler piping and the heat exchanger in this case. So, I'm going to show you what that looks like. These are the charts we're talking about. This is what you need to be able to comprehend and understand, and how to interpret this, okay? Those numbers I just showed you are referencing flow through the heat exchanger based on GPM. Notice this is a little over 7, and at a little over 7, you're only going to have 1.5 foot pressure drop, okay? That's relatively really low, but what delta T is that? Anybody want to guess? For the sake of time, I'm going to go ahead and throw it out there, okay? So I'm just going to do a ladder here, right? I'm going to show you what it looks like at a 30. I'm going to show you what it looks like at a 20, okay? Again, nice round numbers here. I mean, if somebody wanted to do a 25, you could extrapolate and come up with a GPM and that. Here's one thing I do want to point out. Some boiler manufacturers, including this one, will actually throw a little fudge factor in there. It's not really fudge factor. They're actually anticipating a certain amount of piping, valves, fittings, apparatus, incidentals on that piping, that gives you a total pressure drop through the heat exchanger. Now, if you ever just don't put the belt and suspenders on here, right? If you know they make this note here and they're mentioning near boiler piping, then don't add additional pressure drop for that. It leads to circulator oversizing, just like we always talked about. So just remember what manufacturer, look and see. They'll normally say this is the heat exchanger only, or in this case, flow through the heat exchanger and near boiler piping is what this number here is. And you can do a comparative, like maybe I'll throw 3 or 4 different boiler brands out there, look at their 150,000 BTU model. Relatively speaking, they're kind of the same heat exchanger. And then you can look at the differences in pressure drop, and you can kind of tell which one's thrown some additional resistance on there for the near boiler piping and the ones that haven't.
So Rick, let me just clarify. You're saying that the boiler pump for a 155,000 BTU ModCon boiler, if my design delta T across that boiler's heat exchange is 40 degrees, that boiler pump only has to be able to provide a shade over 7 gallons a minute at a little bit less than a 1.5 feet of head pressure differential.
That's
Is
right.
that what that's saying?
That's what that's saying. And got to always remember this, and only at a design condition. Okay.
We can see how really easy it is to oversize a boiler pump now, to the point
Absolutely.
where it is now to the detriment of that boiler's operation.
It is. And that's why the boiler manufacturers are finally putting this information in their manuals, because they get it too. Here's the thing, the boiler manufacturer, I'm sticking up because I used to work for one, right? I'm sticking up for these guys because when they sell you a packaged boiler, right, and they put a pump in there, that pump most likely is oversized. You know why? Because they have no idea what you're going to do with that assembly. They don't know what's happening on the secondary side, or if there's even going to be a secondary side, or if you're just going to use it for domestic hot water generation, et cetera, et cetera, et cetera. So they're just going to kind of, just take a guess at what will cover them for most applications. And that's why you see the packaged boiler pumps tend to be oversized. Believe me, most time, even when they give you a 3-speed pump, there's a lot of times that speed 1 is even bigger than it needs to be. And John's emphasis, I think, shows you that. Okay, there's a reason John brought that up. He's seen this presentation before. He's making points here. Anything else that we cover, John? Any questions? I mean.
Nope. You can continue.
Okay, as I just showed you in the manual, right? I just showed you in the manual. Use that manual from a specific manufacturer, right? Whichever one that is the one you're supporting. And by all means, find somebody you like, find somebody that makes good equipment, and support them. Okay, this is a generalization when you don't have the information. That's what I'm doing here. Take notes. This will help you out at midnight on New Year's Eve kind of thing. Okay. Confirm what the output of the boiler is based on the job specifics. We need to know what the input is. We need to know, is there any D rate for altitude, caloric value, or anything like that? A lot of times the natural gas utility will tell you what their caloric value is. Those who don't understand that is how many BTUs a cubic foot of this gas can produce at that given altitude. Okay, so that's what you want to. That's more accurate typically, because then you have something from the people who are selling you the gas and are putting the recipe together, so to speak. Okay, deduct for efficiencies based on the application. All that means is, what am I doing with this? Is this going to be low temperature? Is this always going to be condensing for the most part? Then by all means, you could use your AFUE number. Okay, if it's not, then use something less, right? For instance, AFUEs to 95, 96. If you know that thing's going to condense the majority of the time, you could use that number in your sizing. But if you say, well, I'm going to do a bunch of snow and ice melting at high temperature, I'm going to do a bunch of domestic hot water generation at high temperature, et cetera, where those return temperatures won't be as low as they could be on, say, a high mass radiant application, then don't use the AFUE. Use something less than. Probably in the neighborhood of 86, something like that, just over the edge of non-condensing, that sort of thing. So anyway, again, the input of the boiler minus the altitude minus the efficiency will some sort of get you to the maximum output of the boiler, and you could size the pump on that. Now, here's what I want you to ask yourself a question. Is the boiler size bigger than it needs to be? John or Dave, where am I going with that question? How often is the boiler the exact size that you need for your application?
I had it once, but also later in that afternoon, I did discover a unicorn and was able to capture him. It was a great day.
All right, you see where I'm going with that. So here it is, real quickly. Let's take the same 155 at a high efficiency AFUE of 95%. So here's the math on that. 147,250 is the result of this calculation here, right? Divided by, I'm just going to use, just for teaching purposes, a 30-degree delta T. I take my 30 times 490 gives me my 1470. So that result of this divided by this, anybody want to spit it out real quick? Most people doing TACO webinars have their calculator handy. What do we get? Anybody?
Not seeing anything, Rick. Oh, we got 10. We got tens. There we go.
Okay. All right. Very good. I didn't give you long enough, but you see where we're going with this, right? Here's one, same calculation with less efficiency, and it slightly gives you a slightly less GPM required. If you're only going to be operating at 86% efficiency, then you don't need to size the pump for anything better than that, right? So again, 155, take this off of there, it gives you this. There's your delta T, there's your constant. You guys are used to 500, just keep using 500. Again, I'm splitting hairs and I ain't got any kind of thing, but for the most part, there's a reason that the number drops, and we talk about that on other webinars, okay? Here's one with altitude. Some people say, well, altitude, you know, again, if you get something from the manufacturer, you go through the steps of proving that you're getting a certain amount of BTUs per cubic foot of gas, then by all means. But like I said, if you get something from the people that supply that gas that say, hey, you're going to take a D rate, then be sure to derate that first. Your derate comes off of that. Then that 155 becomes a 130-200, and then you take your efficiency off of it, which gives you a maximum net output. And that's what you size the pump on. Here's that same math that I just showed you at altitude, okay? So you're 8.4 gallons a minute. John, this goes right to what you were emphasizing before. You know, what if I wasn't, you know, doing you know, something as efficient, and I, you know, look at here, 0.86, that gets me down around 7 gallons a minute, exactly what we had talked about on that last emphasis that you made, okay? So anyway, folks, just understand these boiler circulators should be and can be smaller than you have imagined in the past. Again, to quote my friend John here, we often see the Benford 5000 as just a standard, you know, a boilerplate boiler circulator. Okay, that'd be like our 0013. Okay, we've seen that as that's just a really big pump. And here's the kicker: most of you folks have a real easy way of telling how big the boiler circulator is, and folks, the boiler manufacturer nowadays, remember I said they always are looking at the supply and the return of the boiler's heat exchanger. They're showing you what the delta T is. And folks, if it's not out there where it should be, turn the damn pump down. And if you've already on low and you're still at 10 and 5-degree delta T's, you might want to think about putting a pump that's more appropriately sized in there. Hopefully my point's made. So anyway, so in order to do this right, again, these are generalizations, not having the boiler's manual available on midnight, New Year's Eve, etc. Just we got to have to estimate what the pressure drop of the boiler piping circuit is at that given load. I'm showing you the load being 10 gallons a minute, right? Well, pressure drop of the boiler heat exchanger, if it's a water tube style heat exchanger, it might be 3 or 4 times this number. Okay, always try to look it up if you can get somewhere online. Try to figure out what it is. But these very popular fire tube designs are much lower pressure drop. They're just buckets of water that we're pumping water through. There's not a lot of resistance. And again, a lot of these manuals, if it has to be from somebody else that has a similar one, you could probably use that. In this case, I'm just under 3 foot ahead. As long as that boiler manufacturer did not add for the incidental pipe valves and fittings, then you're going to have to add for that slightly. But when it's appropriately sized, there's not, and relatively short, like most of the near boiler piping is on the primary side of a primary secondary configuration, then it's usually, a foot or 2 foot ahead, maximum. So again, we take things in consideration like, is there a magnetic dirt separator on there? Are there balancing valves that somebody has cut in there? That sort of thing. So you have to, that all has to be considered on that estimate. Okay. So in this case, I got a primary boiler circulator with a requirement of 10 gallons a minute at 5 foot ahead. Voila. I have the ability to come up with a circulator and make sure it's the right one for the job. Of course, I'm putting my best foot forward here with our 0018E for one specific reason. And again, just like I said, this doesn't have 0 to 10 or pulse width modulation yet. Okay, but what I can do with this, as I mentioned early on, is I can now appropriately set the GPM of this pump to what's correct or appropriate for that specific application that you happen to be working on. Okay, remember what we can do with the fixed speed mode of this pump is we can turn it up or down anywhere between 4 watts or 44 watts. Okay, that's what's cool about this pump. And a lot of our competition can't do that. They're still giving you 3 speeds under that fixed mode of operation. Okay, so again, we have just a dial on the pump that you can just, think of it like a volume dial on a radio or a dimmer switch or something like that. We just turn it all the way low is low, 4 watts. All the way up on this pump is 44 watts. But what's more important and more popular is the fact that we can put it anywhere between those two that's appropriate for that job. In this case, let's take a look at it. This is what it looks out like without all those little performance curves at reduced RPMs. But, let's go in. We need 10 gallons a minute. Okay. And we estimated about 5 foot ahead. Okay. That's calculating a curve, a system curve or a resistance curve for this to be something like that. That gives me an operating point that's beautiful. I even got a room to go up, but more importantly, I got room to turn this thing down. Okay, and again, we'll turn it down when we get the feedback from the boiler manufacturer that gives us the delta T under a design load condition. So those are good. You go out on a job, you're just starting a boiler up and it's really cold and you got some really cold water coming back from a high mass slab. You can put that boiler in a design condition. That means the maximum firing rate it's ever going to see under a normal design condition, right? So anyway, that's what we want to try to simulate. Okay. Let's say you got a 0015 E3. It happens to be on the truck. It's midnight, and I can't turn this pump down to what it should be. Then what is the appropriate mode to use? Well, let's take a look at it, right? You can see here that we've got low is a setting of 5 foot ahead under a constant pressure type operating mode. Now, I gave you a caveat when we started here that this is not really the right mode to use, but it works fine as long as you're not anticipating this pump speeding up or slowing down, because it's going to find the resistance of the near boiler piping and the boiler's heat exchanger, and it's going to find its happy spot, and that's where it's going to stay every time it turns on, give or take a little fluid differences in viscosity, right? But it's very slight. Okay, think of it this way: there's not zone valves or telestats or actuators or anything that are going to change the hydraulics that this pump is ever going to see in a primary boiler circ application. Hopefully that rings true to everybody and you understand where I'm going with that. There's the medium head and there's maximum head. In this case, we knew we were at 10 at 5, and that's what you're going to see pretty much. It might move a little bit back and forth here depending on temperature, viscosity, and some other things, or how well you did your estimate. But the beauty is I can come back this way as well. Okay, it'll just find its happy spot somewhere along this line. So we're running out of time. I'm going to go ahead and just remind you of something, that the reason we're emphasizing this, right? There's that same calculation we've looked at already. You see that where we got 10 gallons a minute. But what if the load changes? Remember, 10 gallons a minute was based on a design load condition. What if we're half of that? What if we only have half of the load, which is what these next numbers are representing, right? Then this is how to do the math to anticipate what your new temperature differential is going to be. You take the net and you divide it by your constant that you're using, typically 500, in this case 490, and then by the GPM that you originally designed at. Now we can anticipate a 15-degree delta T. So under a half load condition, I get half of my delta T. But at least 15-degree delta T is a lot better than 3 or 2 or 5, which is what we see in a lot of these conditions. And again, we want those delta T's to be as wide as possible at any given time. There are limitations there, like I mentioned, on bench conditions, etc. But for the most part, this is how to anticipate a fixed speed pump. Now, again, even if I'm using a circulator that has 0 to 10 and the boiler's controlling it, you can't ever go any lower than low. So that's why it's still very important to get the circulator sizing drilled in, get it pinpoint, dot your I's and cross your T's on this thing, because it'll pay dividends in the longevity of the overall system efficiency. So again, keep it as low as possible. That boiler supply temperature, this is a review. We've done this before with you. This is just a little showing you, if I had a 140-degree temperature going out to the system and I designed it at a 20-degree delta T, that shows me my delta T across the system. The question is, what should I set the boiler up for so that I get this 140-degree out here when I actually have a blending happening here? It's actually higher than 140. How do we know how to figure out what it is? We're going to simplify it pretty much. We know that we sized it at 10 gallons a minute based on a certain delta T, right? In this case, it was a 30-degree delta T. So here's how the calculation looks if you want to take notes. The boiler supply temperature would be equal to the load divided by the boiler's flow, divided by whatever constant you used based on the fluid type and temperature, right? And then you just add the return temperature, okay? So that's what this would look like, okay? 147,250 divided by the flow of 10 gallons a minute. My constant's 490. It gives me a 30 plus 120. 120 plus 30 is 150. Or even simpler, you just take the boiler's delta T, okay, that you used, and add it to the system return temperature. So 30 is my boiler delta T that I used, and I got a return temperature of 120. 120 plus 30 is $1.50. And that's just for us folks that don't know how to solve for X. So
I don't know how many times I saw you explain that, Rick, before it finally clicked with me. I was consciously choosing the harder, more difficult, more complicated method every time as my go-to method. But you taught me well.
Well, cool. Okay, well, I'll turn it back over to John and Dave. Try to answer any questions if there are any. We've ate up all of our time, and but we said we'd stay on. So you folks that want to hang out with us a little bit, we'd be glad to do that with you.
There were a couple of questions that came up during the presentation that I wanted to address specifically that kind of really weren't part of the presentation. And one was, would you recommend hydraulic separators instead of closely spaced tees? And the answer I wrote to Brian, who asked the question, was it depends, right?
Yeah.
And it depends on the size of the zones that you're dealing with. If it's just a single big zone or just a handful of zones where the BTU load of the zones are larger than the lowest firing rate of the boiler, closely spaced tees are fine, and that covers an awful lot of your jobs, right? So that makes closely spaced tees kind of your go-to method for mod-con boiler piping. Hydraulic separators really help when the zones are about the same size as the lowest firing rate. It gives you that hydraulic separation plus a little bit of mass. If you have micro zones like you might with a radiant system, where the BTU loads are smaller than the lowest firing rate, then you need to go to a buffer tank. And a buffer tank is really just a big mungo hydraulic separator, right? So that mass becomes really important there. It's never wrong to use a hydraulic separator ever. There's a lot of benefits there because it's made for you, so that saves a lot of time in your construction of the boiler piping, and it's compact, so you might not have the room to build a header. Maybe you want to save some space. So those are kind of the field options. It's never wrong to use closely spaced tees under the right circumstances, and it's never wrong to use a hydraulic separator. So it just kind of depends on what you're after, I suppose.
Yeah. Another thing to remember, some of the boiler manufacturers are still making condensing equipment that are high mass. So what does that do for us?
That's a big help.
That reduces our cycles, and it just it's the only reason, like John mentioned, we're putting a buffer tank in there. We're putting a buffer tanker in there to add mass to a low mass system. And we're saying, well, okay, well,
yeah,
what if I just put a boiler in there that's got the mass that I need? That absolutely can be done. And that's not a plug necessarily. Just remember, there's more than one way to skin whatever you want to skin. Okay?
There you go.
I don't want to offend any feline lovers out there.
Right, there you go. And then there was another question about DHW production means that the BTU of the boiler needs to be higher than the building heat loss. And there's a yes with an asterisk there, because it's not, A, that's not always necessarily the case, and B, if you can certainly, if the loads work out, there are certain workarounds there. There's a formula. If it's what the smaller boiler is going to do is affect the indirect rate of recovery, which is going to basically harm your first hour. It's going to lower your first hour storage, your first hour capacity. After that, the capacity is what the recovery rate is.
Yeah.
So there are certain ways around that. First off, you do the math and find out what your rate of recovery is, and then figure out what you actually need in the DHW load. That'll help you make that decision. And then you can also offset that a little bit by storing, by using a larger tank, all right, storing more water and/or storing that water at a higher temperature and using a mixing valve, and that'll extend extend your first hour rate. So there's ways around it, okay, rather than just saying, well, this is what the indirect manufacturer says, this is what I have to do. It may very well be. It may turn out to be that way. If you've got that, no excuses, I got that 16-person shower stall, so me and my 15 of my closest friends can all shower together, well then, yeah, you're going to have to need that, because you don't want to run out of water on those conditions.
Yeah, cold water is not a good thing in those situations.
No, definitely not. So anyway, let's see. Okay, well, we got a question here about, are you planning to give presentations on boiler sizing, especially for domestic hot water for different occupancy types? Well, it worked out well. Yes. Yeah, exactly. I think that's going to happen, Ali. I absolutely think that's going to happen. And this one just came in from William Sherwin. It appears that using a variable speed primary pump that allows for setting up the flow by delta T versus old-fashioned flow measurement, the cost and time is much less, and the increase in accuracy is worth the extra initial cost of the pump. Yes, that's a statement we've been making for, oh boy, how long? I'd say almost 10 years now. Delta T pumping is by far and away the most accurate and best way to run any hydronic system. We deliver, Delta T is part of the universal hydronics formula. It states that GPM is equal to BTUH divided by Delta T times 500. If you want to vary the speed of a circulator, keep the Delta T constant to what you designed the system to, which is not a crime. By which some people might say it's not a crime. You give the system the Delta T at which it was designed, and then the flow rate is going to have to change in lockstep with the load to whatever the circulator's low end capabilities are. And all circulators do have a minimum speed on them. So yes, William. If you made that comment during Takeo After Dark, we'd send you a T-shirt.
And Curtis also made the same statement or question. He said, "What about using the VT 2218 as the boiler pump too?" So Curtis had said that. Good job, Curtis. Yes.
I had one in my house doing that for 7 years almost 7 years. So 6 complete seasons. That was my boiler circulator, and it worked flawlessly on a condensing boiler, right?
Gotta love it. Gotta love it. All righty. Well, terrific, folks. Any other questions you have? We're happy to stick around, and this is a good time to ask them on Rick's wonderful presentation, or on really any other questions you might have. This is kind of open. This can evolve into open forum time for you. So any questions on anything hydronics or Takeo related, we're happy to try and do our best.
Got 160 of you hanging around for some reason. So
yep,
fire away.
Well, thank you, Laura. Thank you for being with us. Appreciate the comment. Well, our group is bashful. Justin says, thank you. Thank you, Justin. We appreciate you being here. And thank you to everybody else for being here. Again, a wonderful presentation, Rick. Well done, my man. And thank you all for being with us today and giving us an hour or so of your time on a Tuesday morning / afternoon, depending upon what it is, wherever you are. And we are going to look forward to seeing you tonight. If you are interested, tonight we will be doing a Takeo After Dark presentation on the importance of boiler water treatment. It is always a very, very popular presentation. That will be tonight, 9 o'clock Eastern, 6 o'clock Pacific time. You can register for that through on our website, takeocomfort.com. And in addition, tomorrow night, in our regularly scheduled Takeo After Dark, we will be discussing discussing an important question. With variable speed circulators all out there, is there still a place for the 3-speed circulator? I submit that there is. The other two guys may have their doubts, but I submit that there is, and we'll be making the case for that. And hopefully there'll be enough information there to help you out. But you can also register for that event on our website, takeocomfort.com. Click on the training tab, and you can see all of the upcoming webinars we have. And please feel free to sign up for them. We'd love to have you. And boy, oh boy, and as you can tell, we have a good time when we do these, and we hope you do too.
Hey, just wanted to, got a couple of questions from a few people out there. They're asking about, are there any manufactured teas out there? And yes, I did send a link out in the chat section, and I just sent it out in the questions too. But we do have a closely spaced tea manufactured. You can't get any closer than this tea with your 2 feet there. So
if you got any closer, the teas would be behind each other.
Right. Oh wait, they are.
Yeah, wait, they are. Yes.
So actually, if you'd like me to share that, let me pull that up on my screen. I do have it up on my screen at the moment.
What's the smallest primary size that comes in, Dave? I forget.
I don't have that memorized myself, but I will pull it up on the screen for everybody to see.
What he's referring to, folks, commercially, we do something called load match. And this is kind of how we do a monolithic run of pipe around a building and pull off the secondaries. And the secondary would then, in turn, do a specific zoned area with a small pump rather than a valve and balancing and all the other stuff. So anyway, I can't remember how small it actually comes in, but that, yeah,
So
good,
here's
good
basically
picture,
what
Dave.
you're looking at. So
Yep.
here's your 3D rendering of that T. So you have your secondaries coming off the top here. The different configurations are shown up down later in this piece of literature. Let's see here, and basically a whole webinar on what we just did.
Yeah.
And there we go.
1.5 inches is the smallest
Yeah.
size.
1.5 inches.
Oh, I'm
Okay.
sorry, 1.25 inches in bronze.
In bronze. Okay.
We go 1.25 inches in bronze and sweat. And then we have 1.5 inches and 1.25 inches in bronze and sweat, 1.5 inches in grooved, 1.25 inches, and 1.5 inches in NPT. The
Very cool.
smallest. And they go up to 4 inch, 6 inch actually in grooved.
Well, good. Thanks, Dave.
No problem. Little best kept secrets that we have sometimes. Like to show them off.
There you go. Yeah, it's a simple little device, makes it easy, right? And actually, you can't get any closer than in the same T, right?
Right.
Yeah.
Alrighty, folks.
All
Well, hey, questions have dried up, so I just want to give one last thank you for spending your Tuesday with us, and
Thank you.
we hope to see you soon. Hopefully tonight, tomorrow night, or any upcoming Tuesday afternoon. We'd love to have you, and we enjoy your presence. So thank you again for being with us, and thank you, Dave. Thank you, Rick. What a great presentation, and we'll
Thank
see
you.
you all down the road on Takeo Tuesday.
Enjoy.
There we go, right here. Got to get him up, Dave.
All
He
right.
did it. He
There
did
you
it.
go. He did. That's right. All right. Take care, everybody.
Good day.
See ya.
Good day.